Also in 2018, this was the first paper. And then we have other papers, now it's a growing community. And so it's called also dataset condensation in some papers as well, so it's the same thing. Okay, so the question is, okay, so sometimes it's not necessarily distilling a dataset, that process is faster than training a single neural network. So then you may ask me, why do we need it then? So if you need quite a bit of time to distill this dataset, I could just take a model and then train it on the original dataset, and then it will take maybe even shorter. So, so this will bring me the first slide. Basically, in the tasks, when we need to train multiple models multiple times, let's say you do a neural architecture search, hyperparameter search, so you could use this synthetic training set and then train lots of models on it very quickly. And then, for example, you can choose the best model, and then if you like, you can still take the best configuration and then train it on the large data set. And this could save you quite a bit of time. So the other thing is continual learning cases. So in some cases, when the data is coming continually in a stream, we may not have access to the previous data. And the problem of forgetting is pushing researchers to simply sample few examples from the previously seen data. So dataset distillation that helps us to kind of have a very compact set summarizing the previously seen tasks and data quite in a compact way. So it's used also in continual learning. And also in federated learning, let's say we are training a model in a distributed way in several nodes, and we are not allowed to share data across the nodes. In that case, for example, instead of sharing gradients between the neural networks, between the nodes, we could share small synthetic sets. And one interesting thing people have been working on is privacy aspect. So dataset distillation in some cases can also anonymize the data, remove the private information from the data. And this kind of helps us also to do things like, for example, in the medical domain, people don't want to share data sets because there is private information. So there are many attempts on this. So people are using dataset distillation techniques to get a small data set, and then they can share with other departments in the hospital or with public. And then in this data, you cannot really get the private information, so it's usually eliminated. And also, there are more and more things. It has been also shown to, for example, compress social media graphs. So you can take a very big graph and then compress both the structure of the graph and nodes of the attributes of the nodes. So there are many related topics to this. So another way of, maybe classical way of reducing the data set is instance selection. So for example, one way is simply clustering your data, right? So you could just take the k-center or k-medioids in your data, and then we call this core set, and then you can just say, okay, maybe if I take this, so I have this 2D point, this is my, hypothetically, the large data set, I can cluster it and then just use the k-centers, so these 3 red points, to represent the data and then train a model on that. So this kind of models exist. So the difference to what we are going to do is, so the advantage of doing such selection is this can be very computationally efficient. So you could just the clustering can be quite fast and learning these things. One disadvantage is you assume that you can choose very good representative examples, but kind of there is a bit limitation there. You will understand maybe when I move to the dataset distillation, when you synthesize images instead or samples, you can put much more information in that. So you are not limited by the samples in your original training set when you do dataset distillation. And the other thing here is, like, for example, when we do clustering, and we chose these examples, so this is not really customized for the downstream task, right? So for example, if you are doing image classification or some kind of regression, pose estimation, after you have this core set, it doesn't really change how you choose the samples, right? So it's really not customized for the downstream task, this kind of approaches. Another related topic is knowledge distillation. So this was coined by Jeff Hinton. And sorry. The idea here is we have a large data set, and then we have a large neural network. This is usually called the teacher network. We train this model on the large data. And then we can transfer the knowledge of teacher network to a smaller network by kind of optimizing the parameters of the student network to reproduce the predictions of large teacher network. So in this case, we do not really, so this is orthogonal to what I'm going to talk about to dataset distillation. So this doesn't really involve in generating data. It can help maybe to accelerate the training, but you still need a teacher network, and then this can be also used with dataset distillation. There are also some methods, so they can train, so once you have the teacher network, maybe you will not have access to the original training set. There are some methods synthesizing from noise some data to train the student network by using the teacher network outputs, but these are still, these do not focus on generating compact data sets. So the other obvious option is generative networks. So you all know, so we have GANs, variational autoencoders these days, diffusion models, where you can learn the latent distribution of the data set and then sample from it, and then you can generate realistic images, although this image is not so realistic. So here again, the issue is that generating realistic images doesn't necessarily give you a good training sample, right? So it's, at most, if you are generating very realistic images, you can get something like your data set. So it's not going to be, each instance will not be more informative than the original samples. Okay, so I will jump into directly to the methodology. So we have in dataset distillation, kind of, the methods we use can be grouped into 3 categories. So this is a bit inspired from the journal paper I will show you. We have a survey in the dataset distillation. So in the performance matching, as before, so we have this network we train on the large sets, and then and we also have our distilled set, and then we train neural networks on both of them. And then when we test them on a test set, we would like to get similar performance. But in reality, of course, in training time, we are not allowed to check whether we are getting the same performance. So what we can do is, we can see, for example, if we take the model trained on the synthetic set, and then we can compute the error on the large original training set, and then look at the loss. And then ideally, we want this loss function to be similar to model trained on the original set. But actually, what is better is, probably it's better to just minimize. So we really want to minimize that loss on the original training set rather than trying to make it similar. So if we can make it even smaller, it is better for us. So first method I would like to talk about is this original dataset paper. So the idea is, first time, this was the first paper showing that we can learn a synthetic set and pixels of the synthetic set directly. So we start with a randomly initialized synthetic set, so shown with S here. Then we have a loss function, and then we take a neural network from scratch and then train it on it for few iterations, and then minimize the error on that. And then we go to the large data set and then compute the error on this data set. And then we get this loss function t. So ideally we want this LT to be minimum. So this means that synthetic set is, if you train a model on that and then go to the real training set, it can minimize, it can classify all those images in the training set well, so which is what we want. So in the formulation you may see something interesting. So this theta s is function of the synthetic set. Why is that? Because actually it depends on the initialization of the neural network. There is a bit stochasticity in the process because we are using SGD, but it's function of S because it's trained on S, right? So it's kind of, if you fix the initialization and then fix your random seed and so on, so the theta S, the parameters of the neural network depends on the synthetic set. So the authors use this idea, and then once you have that observation, you can, in the back propagation, you can compute the gradient backwards, and then so you could you need to do is you can go back to the synthetic set, but to do that you have to unroll this computational graph. So we were doing few iterations of stochastic gradient descent. So you have to really go from the loss through the neural network and then unroll this computational graph, and then you can update your synthetic images. So this is actually, it can be shown as a bi-level optimization problem. So it's basically, you want to minimize the training loss with the network which minimize the loss on the synthetic set. So, so this was really great. So because I talked about instance selection, here we are really learning the pixels directly, and in the instance selection we could only choose one of the few of the original training samples. So this is much more flexible and powerful. So the challenge here is that unrolling this computational graph can be expensive because you will have lots of gradient terms, and then it will depend on each other. So there is like quite a bit dependency. That this is an expensive process. And then what the authors did is, okay, so we cannot have lots of iterations here. So because of that, they kind of keep this inner loop iteration. So in the inner loop, we are learning the theta s on the synthetic set. They kept the number of iterations few. So this is a problem, and then in the more recent papers, based on this observation, what people are doing is we could, for example, take our model, split into a feature encoder and a linear classifier on top of it, and just learn the linear classifier in the inner loop. So the advantage of doing this one is we have closed form solutions. For example, you can just do here, I'm showing some regression formulation. So you could, and then you could just learn this linear layer doing regression, and then we have a closed form solution. You can do this one very efficiently. Sorry. The other paradigm I would like to talk about is parameter matching. So in parameter matching, we do something even more constrained. So we do not only want to get similar performance with the model trained on the large data set, we also would like to get a similar parameter, similar solution with the model trained on the large data set. So this kind of implies if your function is smooth, it's a smooth function, you should be able to you should be also getting some similar performance as well. So one way to kind of formulate this one is, let's say we can offline pre-train our one model on the large training set, which is shown with theta t, and then we can take the other model, train it on the small synthetic set, and basically to minimize the loss function on the synthetic set. And at the same time, when we do this, we would like to get the same parameters. When you update your theta s, when you get theta s, we would like theta s to be similar to theta t. So basically, you want to get the same parameter. So it is again, so you can write it as a meta-learning problem or bi-level optimization problem. So we are now, instead of minimizing the error on the training set, we are minimizing the distance between two networks. Of course, we are not updating the theta t parameters. They are already frozen. We just computed once. And also, we want to produce the theta t. So theta t will be different based on the initialization. So we want to kind of make sure that whatever, like with any initialization, we should arrive to the same solution. So compared to the performance-based previous method, the advantage of doing parameter matching is you kind of get more supervision, right? So instead of just trying to minimize the loss, you want to really regress the parameters. So it is like very high dimensional supervision. But the issue is this is very difficult to optimize. And the reason is like if you train your model on the large data, so it will be quite far from the initialization. It is initial values. So to take the model from random, train it on synthetic set, and then reach to that particular solution is a very difficult optimization problem. There are lots of local minima along the route. And also still we have as in the previous one, we have to still unroll this SGD step because we start from this loss and then go back, unroll these SGD steps, and then update our synthetic set. Okay, so the one way to kind of make this problem, improve this problem is we could say we do not want only the same solution, but we want to also have the similar solution path in the parameter space with the model trained on the large data set. And the idea now is, so at each iteration, we train one model on the large training set, one model on the synthetic set, we update them, and then we compute the difference between them. So now the parameters are not too far from each other because we are just taking the checkpoints. But again, and then we update the synthetic set. The issue is it can be very expensive to do this because we are training two models at the same time. There will be lots of dependencies between the parameters. So one simplification we can do is we can assume that, so we initialize both the networks with the same values, same initialization, and then we can assume that if our method can optimize this parameter matching function loss well, we actually theta s can follow theta t well. So we can say, okay, let's discard let's discard this previous theta s t minus 1 and theta t minus 1, because we can kind of optimize and make them very close to each other at each iteration. And then if you do this, what becomes, so this simplifies the problem quite a bit, and then this becomes a gradient matching problem. Basically, we can just compute the gradients with respect to the parameters in both networks, and then minimize the difference between the gradients. So the advantage of this one is, first of all, we are following the path, so this will be easier to optimize. And the other thing is, actually, you don't need to keep track of the model. You don't really need to train another model on the large training set. You just need to compute the gradient of on the original data set. So this kind of simplifies the computation quite a bit. So we are just computing two gradients given the samples from synthetic sets and training sets, and then minimize the difference between them, then update our synthetic set. Okay. Maybe I can just ask, is there any question? Okay. Okay, so I should maybe speed up a bit here. So how many minutes do I have? Is it?
12 minutes.
Okay, so okay, maybe I will very briefly summarize this one. So one issue here is that actually the assumption of we can optimize the difference and minimize the difference between two doesn't hold so well. So this was observed by another paper, and then the authors suggested actually doing the real thing. So it's basically if you just keep track of two models and then minimize the parameters, you can get even better results. But this is computationally more expensive. So finally, there is distribution matching. So this came out actually in a way that if you look at instance selection, so it is fast. It doesn't depend on the architecture problem, but it's heuristic, and it's limited by the original samples. At the same time, dataset distillation can be slow, architecture dependent, but optimized for the downstream task, and it can synthesize more compact samples. So we thought, can we kind of have the best of two worlds? And the idea came out like this. So let's say we are training a model on the large data and then small synthetic set. And these blue points are, again, the samples, sorry, actually embeddings of the large training set. So what we do is what I show you in the instance selection. So we would like to match the data distribution of the training set in the embedding space. So this green points with the red circles around them are basically embeddings of the synthetic set. So basically, if we can produce the same data distribution, which is shown with case answer here, then this can give you good synthetic samples as well. Maybe I will not go through this one, but the advantage of this technique is kind of we are learning a synthetic set which is the same distribution with original training set, and different than instance selection, we are synthesizing these samples. So we are not choosing these instances from the original set. So far, I just talked about learning the synthetic set pixels directly, but actually we could also use generative adversarial networks or newer ones like the other models. So so the idea is so we could, for example, take a set of latent vectors and then generate some images by using a pre-trained GAN. But the issue there is that these images will not be informative or compact for training. So we would like to actually optimize them as well. And what we've shown is basically we can take the synthetic set, feed it to a network, and then again take the real training set, feed it to a network, and then we can learn to match the distribution as I shown you in the previous slide. And so the only difference here is that we are not optimizing the synthetic set directly, but we are optimizing the latent codes we use to generate the synthetic samples. So why is it better? I think it depends on your requirements, but let's say if you have a large synthetic set, I mean large is relative, so you may need less storage if you are just storing the latent codes and the GAN parameters rather than keeping all the synthetic set in your disk. But also there are other advantages. For example, you can transfer generative models trained on large data sets and do this. And the other thing is here, GANs have some advantages here. Kind of parameters are shared when we are generating different images. When we are generating a synthetic set, learning the pixels directly, we do not really share much between them, so through only gradients. So there can be advantages of transferring knowledge between them through parameters. Okay, very quickly, so I just talked about learning the images, but you could also learn the labels as well. So for example, you can make from one hot vector, you can make them soft distributions, and this has been also shown to improve the results. Along with the samples, you can also learn them. Okay, I will just move. So how we evaluate these things, dataset distillations, is typically on small dataset so far. So we first, in the stage 1, distill the synthetic set. In the second stage, we train a model from scratch on the synthetic set, and then we test these models on the original test set. So we typically report performance with different synthetic set sizes. Also, we report something like, so in stage 1, we use one architecture. In stage 2, we use another architecture. And then we show whether it generalized to unseen architectures before. So maybe if you haven't seen how do these images look like, so this is from one paper, you will see that actually you can recognize the synthetic samples, the categories in it, but they do not look necessarily realistic, but these are like informative to train models. And you can see certain artifacts, and of course they are difficult to interpret. We can't really know why it's exactly that way. So yeah, it's most of the time, if you take these images and then apply a classifier on them, you could see that you can either identify them. In some cases, it's harder. Like in this image, for example, the logits are quite small for all categories. It doesn't mean that they are bad. Very briefly, so I'm showing this performance-based techniques and parameter matching and distribution matching one. So the most recent one is doing this performance-based with this kernel-rich regression. This is FREPO that performs best. There is not too much to say there, but so far I was showing the results with 10 images, 20 images per class. These are actually, so normally you have in the original set 5,000 images per class. So these are huge compression ratios. Even 50 is 100 times less. One thing we see is actually if you use more and more images, so here you can see the upper bound, so this is the model trained on the whole data set. And also you can see like this instance selection methods, for example, this random k-center. So you could see maybe the k-center, it's the green one. So what we observe is for few images, when we have a very small synthetic set, dataset distillation methods do really well, perform much better. But when we have more and more images, actually the difference between these two, instance selection and dataset distillation, is quite small. So how many minutes do I have? So,
Around 4 minutes.
okay, so one open direction, so if you're interested in doing this kind of research, is how do we kind of reduce this gap, and then how can we get maybe at some point the same performance with the whole set training but much faster. So there is a recent method, it's doing some heuristics when learning the synthetic set, so this can be one direction. So what they do is they start with large crops in the synthetic sets and then focus on smaller ones and smaller ones. So what this does is actually gradually encodes more information in the distilled images, so it's easier to optimize. So it's, at the end, you are really squeezing lots of information to a small patch in the distilled image. So this kind of helps to close the gap quite a bit, but there is still quite a bit things to do there. You could also see, I don't have much time, so if you train your model with one architecture and then use this model to train another architecture and test this result, these models are usually quite sensitive, so these are the original architectures. Once you move to other architectures, the performance drops. So this is another open question. How do we have architecture agnostic? So representations and methods. So this is quite crucial if you want to do neural architecture search. Also, some of these models can be very expensive to train. They may require lots of GPU memory because of this unrolling the computational graph and so on. So one way it is recent is you can decouple the training of the model on the original set, and then you can kind of just use the statistics from the parameters of this model while training the synthetic images. So I will not be able to go into that, but the idea there is like you kind of decouple the optimization so you can do them separately, optimize them separately. So this is another way of kind of scaling up. So actually this paper, NeurIPS 24, show results on more modern data sets like ImageNet and so on. So I have 3-4 more slides. So the also dataset distillation methods have been mostly used on image classification and or just classification problems. But actually we have lots of important problems like semantic segmentation, depth estimation, pose estimation, all these problems in computer vision. So this is also quite important to kind of move away and go beyond the image classification. So one idea could be like using generative models. So for example, in one paper we shown that you could kind of get a generative model and learn a annotator small model, looks at the generator weights and then labels gives you the part segmentation of the generated images. So you can optimize this thing like in the dataset distillation methods in a way that when you optimize a model on this synthetic set and the labels, you want this model to do well on the real segmentation data sets. So by doing this, you can learn to generate labels for synthetic images, and then you can make them also more compact. Okay, so also, so far, it has been only shown on single modality. So there is a recent paper showing that you could also do vision and language tasks and doing this, how do they call it? Like the bimodal trajectory matching. So basically, they learn, instead of learning a single image, they learn an image plus the caption. So, and then once you have this distill set, you can use this data to fine-tune models quite efficiently. Okay, so this brings me to the end. So I think my message has been, I think efficient model training has been becoming increasingly important in the big data era. And then we have quite a bit interest in dataset distillation. You can see the citations in the first paper. You could see this workshop. There will be a challenge in the ECCB, for example. We have a very good starting point, a survey, quite nicely written. So and there are lots of open directions. So I hope I can convince you this is a worthy pursuit, and then you can work on it. Thank you very much.
Any questions? Yep.
Thanks for the presentation. How can we extend research for object detection? I mean, if there are more than one object in a patch, and in your case, you only have one classification, but in normal scenarios with object detection problems, there are maybe multiple objects. So how can we tackle this?
Okay, so the question is, how can we extend it to object detection? So in object detection, we have boxes and the labels of the instances. So we could also kind of, let's say, choose some regions in the synthetic samples, right? So then we could basically do the image classification on those patches. I mean, this is the first naive idea, but of course, you could also update the location of the instances. We have this differentiable functions. They can map the locations of boxes to images, image features. So I think that can be a good starting point.
Yep.
Train a model on it. Do you think if we train on a distilled dataset, the model would probably generalize better since it has seen all the domain-specific features of the original dataset?
So the question is, can it go beyond the performance of original?
Exactly. Other domains, since we train on the smallest dataset possible.
I suppose like. If you manage to, so let's say in training samples, let's say, what I can think of is like if you have outliers, let's say, maybe when you distill your training set, you may eliminate the outliers. So this can be one thing you can improve with dataset distillation. But other than that, I'm not sure, because unless you bring some external knowledge, it can be a bit difficult. The only thing is like maybe eliminating the noise in the training set somehow can help. So if you are transferring like existing models, for example, like generative models and so on, there can be more information coming from there as well. So it can generate maybe even more informative images than the one in your training set.
We have some information about the target dataset that belongs on model, which would be good part of time. Can we, for example, but do you think it's possible to do kind of targeted distillation, where we're gonna distill our source domain, or the source dataset, in such a way it becomes closer to the target one by like removing the noise you said?
So that's a very good question. So it's kind of like you do almost domain adaptation, right? I think that was I wanted to mention that as well. So that I think. There is like, just very briefly, there is this in the label distillation part, this is like a toy problem. What they shown is like, they have this amnest, these are like Latin letters, and by just updating the labels, they could learn to classify the Japanese letters actually. So they are doing again meta learning. So they are using these images, original images, but by modifying the synthetic labels, they learn to classify Japanese ones without training on them directly. So yeah, but that will be, I think, yeah, one thing people haven't explored yet. Yeah.
When you're going through the stage one, distill the synthetic data set
Uh-huh.
stage, it seems like you assume all of the data is annotated. You're just trying to save compute later. Is there a way to kind of release that assumption
Mhm.
and think, I don't have everything annotated, and what I'm also trying to do is limit how much annotation I have to do on this data set?
Yeah, that's a good question. So the question for the ones in Zoom is the original data set may not be labeled. Can we still do that, use it? I think it could be interesting to use, like, for example, loss functions from self-supervised learning and so on. So it can be, we could have a supervised loss function on the labeled ones and self-supervised loss function on the unlabeled ones. And we could still, for example, try to produce similar kind of loss functions on the unlabeled ones and on the synthetic ones by, for example, by comparing crops with each other and so on. So that's a good idea. Yeah.
You mentioned that the dataset distillation technique was created using a single model and it may be architecture dependent. But you also briefly mentioned about testing the distilled dataset on other architectures and
Right.
drop in performance. And I was wondering if you could elaborate just a little bit more about how large is that drop in performance if you test it on a different architecture? Are there certain methods that are less sensitive to that, that are more architecture agnostic, but still good performance?
Yeah, so that's one of the challenges in dataset distillation. So we do not want the synthetic set to be too dependent on the architecture which is learned on. I think more recent methods are more robust to that. One challenge there is what people observed is like the normalization you use in the neural networks matter a lot, and I think because of that there has been quite a bit improvement. And then where this comes from is actually, so typically we use batch normalization to train models and so on. In synthetic samples, because the synthetic set is a quite small set, using normalization is causing headache there because you cannot get accurate mean and standard deviation and so on. But definitely the new models work better, but still there is a significant performance gap there. But having said that, one last thing, I think I should leave the space to the next speaker. But it has been shown to work on neural architecture search quite well. So it's not too bad actually if the changes in the architecture is small. Okay, thank you very much.
Let's thank Dr. Bilal once again for his lecture on basically, which was an introduction to data set distillation challenges and approaches. Let's thank him once again. Our next key speaker is Dr. Philippe Isola. Brief introduction about Dr. Isola is Dr. Isola is an associate professor at EECS at MIT. His research interest is on computer vision, machine learning, robotics, and AI. He completed his PhD in brain and cognitive sciences at MIT and has since spent time at UC Berkeley, OpenAI, and Google Research. His work has particularly impacted generative AI and self-supervised representation learning. Dr. Isola's research has been recognized by a Google Faculty Research Award, a PAMI Young Research researcher award, Samsung AI Researcher of the Year award, a Packard fellowship, and Sloan fellowship. Yeah, we have Dr. Isola here. Yeah, thank you. Everyone. Oh. Yeah, yeah.
My mouse.
Okay, we do also.
Mhm. Can't see my mouse, so I'm just trying to minimize this. Place that. Wonderful there. Okay, let's try this. Okay, got it. Okay. Great, yeah, thanks for inviting me. I think dataset distillation is one of the coolest ideas that one of my favorite ideas of the last 5 years or so in computer vision. So I really love this topic, but I don't work directly on it. So I'm going to talk about this problem setting of how could you possibly learn computer vision if you don't have access to any photos? And I think it's very related to the dataset distillation problem. But most people are doing big data. They're doing, let's collect 400 million images, 6 billion images, whatever you want. N goes to infinity, but this talk is about N goes to 0. What if you have no images at all? Okay. And this is work with a bunch of other students and postdocs, and also joint work with Antonio Torralba's lab. Okay, so the first question is what counts as visual data? So what am I talking about here when I say no visual data at all? So, okay, on the left is going to be visual data, and the normal one is photos, but I'm also would include in visual data computer graphics, generative models that make realistic imagery. So there's going to be a blurry line between what is visual data and what is not in this talk, but I just want to make it a little bit clearer up front. What is not visual data is language or code or math. Okay, so language, this is a quote from the story of the Madeleine dipped in tea, a kind of famous excerpt about the sensory experience. And you can see that the language is very visceral and evocative of that sensory experience. So language isn't pixels, it's not visual data by my definition here, but it might be highly visual in its imagery and its reference. Code is not visual data, but code could render visual data. So it's a little bit, but anyway, this is the basic distinction that I'm making. Okay, so can we train on this kind of data on the right and get good images from that data on the right that will train a computer vision system? So I'm going to talk about each of those types of data, and I'll start with talking about learning from math, data from math. Okay, so this section is motivated by this finding that neuroscience scientists have made that in the animal retina, when it's developing in the fetus, there is spontaneous top-down activation, and it looks like this. Okay, so this is a recording of an animal, a fetus's retina. It's, I don't remember which kind of animal it is, but it's not a human, it's another animal, I believe. And you have these really interesting patterns. Okay, so there's no light coming into the system at all, but the system is making its own data. Okay, so this should look like dataset distillation to you. The system has come up with a kind of developmental pattern that makes data that possibly could train up the early connections in the visual system during development. And that's what neuroscientists have speculated is happening. I think the evidence is still a bit unclear, how far that goes, but there is spontaneous activation that looks like sinusoids and visual patterns. Okay, so could we make that kind of data? We'd come up with simple equations that if you run them and then you train on their outputs, you get good computer vision systems. And the first paper I want to talk about is this one, Learning to See by Looking at Noise, that we published a few years ago on that topic. Let me see if I can minimize this. Nope. Okay, just do this. There we go. Okay, and this is work led by Manel and Jonas and Tongzhou. Okay, so the paradigm that we're going to be using throughout this talk really is going to be contrastive self-supervised learning. That's how we'll be learning our visual representations. And I think many of you would be familiar with this at this point, but you can do that by taking an image and just extracting patches and training a neural network to classify if the patches come from the same image or different images. And you can do the same with any type of visual data generated by a noise process or a mathematical process. So here I might have some kind of retinal wave-like data, and I can chop it up and try to classify, did those two patches come from the same image or a different image? So this contrastive learning method will be our vision system. We're going to look at what kind of data sources can effectively train that system. Okay, we're going to evaluate our success on standard kind of representation learning metrics. The main one will be transfer to ImageNet classification. So the name of the game is come up with a representation, like pre-trained visual representation that transfers well to linear classifier to ImageNet. So the y-axis is how well does the classifier do on ImageNet. And we're going to be making bar charts comparing different methods, so different pre-training methods on different types of data. Okay. To give you a baseline of where you might start, okay, well, I said that we want to learn with no data at all, right? No visual data. So the obvious starting point could be that you just randomly initialize your neural network. And if you do so, you get about 20% accuracy by this metric, okay, using the architectures that we have in this work. And as kind of an upper bar, let's say you're just using real data, you're using your full data set. You're using some data set of natural photos, not ImageNet, but a different adjacent data set places, then this is how well you do. So we're trying to increase from that baseline of random init and get as close as possible to if we use real data. Maybe in theory you could surpass real data, but we're not going to do that today. Okay, so those are the lower bound and upper bound. Okay, so this random initialization is actually not that bad. 20% classification accuracy on a 100-way classification task is actually not that bad. So one way of seeing that is that we could take a set of photos and find and embed them into a representation using our random networks. It's just a random embedding, a random network embedding of these images, and then find the nearest neighbors of those images in a data set, in the ImageNet data set. So here are our query images, and here are the k nearest neighbors, the 5 nearest neighbors. And this is a random networks embedding. It's not actually terrible, but okay. It's got red, basically matches colors, so it's doing something, but whatever. 4% accuracy on nearest neighbor classification. Got one lobster at the top there. It's kind of interesting, it's already doing something. Maybe the inductive biases of the network architecture are helping it here. Okay, but it's not matching, 2 birds to birds, it's matching them to sky and water. Okay, so let's design some noise processes and see if we can train on those noise processes, these retinal wave-like processes, and see how effective they are. Okay, again, and I referred to this as learning, vision from math, from equations. And so the noise processes are all going to be described by fairly simple equations or simple algorithms. And the first one that we're going to exploit is you can think of a million different ways of generating noise that has good properties to train vision, and the most classic one might be this property that natural images follow this 1/f power spectrum. Okay, so in the Fourier space, the power spectrum has this kind of nice 1/f shape, this power law shape. Okay. So how can we make images that have 1/f power spectrum? It's pretty easy. I can take white noise on the left, and I can take the Fourier transform, and then I can just multiply the power spectrum by 1/f with maybe some different coefficients for the x direction and the y direction, and then I can do the inverse power spectrum to get my generated imagery that now has that property of natural images. Okay, so it's just a very simple way of making these random noise images that look a little like real images. This is our proxy for real images, okay? This is like the distillation through humans of how the world looks. Okay. Okay, so how well does that do? You can start to kind of guess and think, okay, probably should not do that well, but we saw random already did okay. Okay, so it's okay. Like you already got a 10% boost just with this tiny little property of natural imagery. Okay. I mean, think how many billions of photos you need to collect to get a 1% boost now on a hard data set. It's not trivial, but back, at the low end of the classification range, you can get big boosts very quickly. Okay. So another really cool property of natural images is that the colors tend to be really sparse. So most images only have a few dominant colors. And you can exploit that by basically taking your white noise, modulating it with this 1/f spectrum, and then additionally having a little tiny probability model of how the colors are distributed within the image. So it's going to be we sample how many colors we want, and then we sample what the colors are from some kind of uniform distribution. Okay, and then we just do a kind of histogram matching process to change the color histogram of our 1/f image to the color histogram of a sparse kind of color domain. So here's what that looks like. Now each of these images only has, maybe a few different colors. So it's not quite as chaotic. There's, some interesting aesthetic structure there. Okay, so tiny little change, how well is that going to do? And another, 5% boost. So we can keep playing this game. Okay, another classical process for making random images is called dead leaves. It's meant to look a little bit like if leaves are falling in the fall and they layer over each other. This is capturing the idea that images have occlusion structure in the natural world. If I take a photograph, then things will overlap and you'll get all of this type of structure. And dead leaves was a old, many decade old model that tries to look at that. Okay, so I won't go into the details of all these methods, but this is what the images look like. It's 50 lines of Python to make an image like that. Here are a bunch of samples. You can change the parameters. We can say I want the components to be not square, but rotated squares or rectangles. I can make them circles and triangles. And some of these do okay. And as I make them more complicated, add rotation, add different types of shapes, they get a little bit better and a little bit better. Okay. So let's look at our nearest neighbors again, just to check where we are. Okay, so remember the lobster got matched to red items, happened to get one lobster correct. Okay, it looks like we might have taken a step back. We didn't quite get the colors. This is trained on dead leaves now, but we started to get something kind of interesting. We've got a robin matching to two robins. We got birds matching to birds. It looks like the semantics might be starting to get a bit better, and that's reflected in the accuracy, which is now on this metric, 13%. Okay, we even got a lorikeet up here on the second row. Okay, another thing that we could do is we could say, another interesting way of generating random imagery is to take a generative model that's not trained, but is just randomly initialized. So in this is a few years old, so we took the StyleGAN model. So rather than training it to make faces, we just initialized it randomly. And if you initialize it randomly in the right way, it will make these interesting patterns. You're basically exploiting the fact that this network has good inductive biases, that has notions of, it has local filters which build up over space. Okay, so StyleGAN will generate at initialization images like this if you initialize it with nice kind of Gaussian and orthogonal filters. Okay, so how well does that do? It's untrained. Okay, so we have a few different versions of that, but the one with oriented filters rather than like isotropic filters, strain initialization does decently well. So these networks in their structure might have pretty good inductive biases for vision. Okay, nearest neighbors for StyleGAN trained model. the lobsters now, we've got 4 lobsters, right? Okay, we're getting somewhere. We're making progress. Okay, but I don't have the best one next yet, so I'll show you that soon. Okay, I want to do a little quiz. So how can this be working? It doesn't quite make sense. Like, didn't we need rich semantic data sets? Don't we need the internet to solve computer vision? How can we do it, at this level, which 10 years ago would have been like almost state of the art, without the internet, right? These numbers are at the level where maybe not 10 years ago, but 20 years ago, I think they would have been, state-of-the-art computer vision systems. And we didn't use any photos from the internet. That's kind of crazy. And I think it can be pushed farther. But here's a glimpse of patches that are the input to the vision system, the contrastive learner, that is being applied to these different types of data. And some of these come from real photos, and some of them come from noise. So this is what the vision system sees to train itself. So I want to do a little quiz. So who thinks number 1 is a real image or a noise patch? So raise your hand. Actually, let's do clap. Okay, and then number 2, clap if you think it's real. Real. Yeah, okay. 3, clap if it's real. Okay, 4. No one thinks. 5. Everyone thinks. 6. No. 7. Most. Okay, you're pretty good, but not perfect. So 3 was real. Actually, it's just a little bit oversaturated. But this is exactly what MoCo V2. That was the model at the time. Those are the patches it sees that it tries to learn from, and they don't look that different in noise. So that's the point I wanted to make there. Okay. Okay, so I'm going to now move on to actually. So any questions about that project? I'm going to move on to another iteration of that project. Yeah. Yeah, fractals do okay. There was another work that preceded this work, which was learning from fractals, and it didn't actually compare that well on the benchmark that I showed you. But I think there's probably a way of making that work well, because the space of fractals is pretty big. So I think you have to get the details right, but there probably is a way to make that work really well. George? Yeah, good question. I don't know if we ever tried that. It's probably in some supplemental material somewhere. I don't remember, but I bet it would. Yeah, I'm pretty sure Minil he'll know the answer if you're interested, but he probably tried it. It probably didn't help much. Otherwise, we would have highlighted that. Yeah.
There was this paper about saying that neural networks learn the shape, texture, and so on.
Yeah.
What do you think with this kind of images it learns? Does it learn? To me, it looked like if it learns textures more.
I think that might be related. So neural nets might be texture biased or find it easier to learn from texture. And these noise processes are kind of capturing the texture-like elements of vision, but probably not the more geometric and structural properties or like a long-range geometry. So that might be one reason why this was somewhat successful. Okay, let me move on to the next one. It's the continuation of the last project, but we said, okay, so if we can write these simple equations that make noise that can train a vision system, could we write fancier code that makes fancier noise that trains a vision system? And I think this one is really related to dataset distillation. The question is basically, what is the shortest program that yields vision, right? The machine learning algorithm that we run to train a contrastive learner on a data set is a very short, simple program, just gradient descent, backpropagation. But the data is not necessarily a short program. The data is incredibly complex if it's the whole internet. But maybe we don't, there might exist a short program that could replace that data. And the short programs we looked at are what are called shaders. There's a huge community online that makes these for fun. So they try to fit them into a tweet sometimes. This is a tweet, and that tweet, if you render it through the OpenGL shader language, makes an image like this. Okay, so it's how long are tweets? So 280 characters or something like this. It's not much data, but it generates this level of complexity. And you can imagine I could train my system on that, just like I could train an animal on retinal waves and get some elements of vision. Okay, so this was the next work from Manil and the team. And we downloaded a bunch of these shaders made by humans. Okay, so there is this source of like humans curating data, but there's a lot of that online. And they all make these different interesting patterns. Okay, so 21,000 different shaders of this type we downloaded. Humans made each of them, and most of them are hundreds of lines or hundreds of characters or maybe thousands of characters for some of the longer ones. Okay, so these are just some statistics. I won't go into the details on that. Okay, but this is what the data set looks like. So each of these images in the montage is one frame from one of the shader programs. And it's a really interesting community. If you haven't seen it, check it out. Like the amount of visual complexity and art you can get into, 280 characters is amazing. It's this came out of this demo scene community that's been around for a long time, trying to make interesting computer graphics and very short programs with only like a few bytes or kilobytes of data. And just to show you a few of them. Okay, so there's a little bit of a sleight of hand here because the OpenGL shader language itself codes certain properties of the world. So for example, OpenGL knows how to do 3D rotation and camera projection. And so you're kind of giving the system that. Again, it's not a lot of data, it's not a lot of algorithmic complexity. It's a short program that OpenGL is a short program itself, but this is something to keep in mind. Okay. Okay, so how well do you think it will do? I think you probably know, right? I'll put it at the last, as the last bar. So here we go. Almost getting to the level of training on real photos. Okay, remember, this is 2021. We're running models and architectures from like 2015. This is not state of the art. This is not the most competitive benchmark. This is more trying to be kind of an exploration, a scientific investigation. But within this setting, this somewhat narrow setting that we chose, ImageNet 100 transfer learning with a linear classifier on a ResNet backbone, we're getting close to matching training on real photos. So I think that's something. Okay, it's maybe more interesting to look at the nearest neighbors. So if we train on these shader images, then our nearest neighbors look like this. Okay, so now lobsters are all lobsters. The lorikeet is all, it's not just lorikeets, it's two lorikeets matches two lorikeets, right? A guy with a lobster matches a guy with a lobster. So, okay, ImageNet 100 is a data set of 100 categories. So one of the categories is lobster, and there'll be a lot of photos of guy with lobster. Some of this is kind of photographer bias. It's making this look better than it might really be. But nonetheless, like if you showed this to computer vision folks at CVPR 10 or 15 years ago, I think it would have been like a strong result. Okay, trained on noise. Okay, so what you might have the question, what is the best program? What is the best tweet that can train a vision system? And here it is. So of the 21,000, this is the best one. So as you're watching that, your brain is getting pre-trained to be really good at ImageNet classification. So if you train your brain with a linear classifier on ImageNet 100, you'll get 36% performance after watching this movie. Well, that's what the machine does. Okay, so this is a longer program because the best one happened to be, it tends to be the longer the program, the better the data quality. There's a kind of small correlation there. And so to get this level of complexity, we need 2,000 characters, a little bit more than a tweet. Okay, maybe a tweet thread. Okay, so now for the last section of the talk, I'm gonna talk about the latest project, which is actually at CVPR this year, which is trying to learn how to see from language data, from language models. Okay, and again, the intuition for why this should be possible is that there's a lot of visual information, a lot of visual imagery and evocative descriptions inside books. For example, the Proust description of the Madeleine dipped in tea. And another reason why this could be possible is these language models are trained on code that might quite explicitly describe visual data. So these language models are trained potentially even on in a text file that says the left pixel is red and the next pixel is orange. It could have like raw RGB data in the form of text. So that would be kind of like a raw language representation of the imagery. But nonetheless, this is text, this is language, this is not using any real pixels. Okay, so this project is called Vision Checkup for Large Language Models, or for language models. From Pravyusha and Tamar are the lead authors, and it will be presented later this week. Okay, so we asked two questions. One is, can language models draw images? And the other is, can language models interpret images? And these, let me just clarify, these are not VLMs, these are not vision language models. These are pure language models. So we look at models like GPT-3, which are, we're pretty confident, you can't be sure with OpenAI, but we're pretty confident those are not trained on visual data. We also compare it with GPT-4. That one, there's some chance it's contaminated with visual data, but still it's a language model. Okay, so can language models draw? Okay, so I'm sure a lot of you have seen cases of this before, the famous unicorn example from about a year ago. And we wanted to look at that in a little bit more detail. So we prompt a language model with this, return code and processing. Processing is a computer graphics language to draw men herding sheep. And the output is code. So the language model knows how to map from strings to strings that can output code. And then we can run processing on that code and see what it made. Okay, so that's the basic setup. And they're pretty fun. Like this is a fun game, and a lot of people have tried this online now. Okay, so we made a big data set to try to probe all the different types of visual knowledge it has. Is it good at shapes, at colors, at semantics, at layout, objects and scenes? I really like this. Okay, this one here. So I'm pointing at the bottom row, the middle column. There's these cars that are driving on a road, and you can't quite see, I didn't quite zoom in, but they're a little bit blurry. And that's because the prompt says, cars driving quickly on a road. It's actually rendering motion blur by like overlaying a few different cylinders or ovals, I suppose. Okay. So language models can generate imagery by generating the code that renders the images, and it can make very diverse imagery of all different types. So the paper quantifies some of the properties of that imagery if you're interested. You can really think of this as like having quite a diverse concept of how things look. So you can sample multiple times, you can randomize the prompt in various ways or do data augmentation on the prompt, but you could also just sample multiple times and get all these different varieties of strawberries. So this is a way of making data from language. Okay, and different models will have different fidelity in their ability to make images that actually look like the object they're trying to make. So this is on the y-axis is kind of a certain type of clip score, which is saying, did I actually make a strawberry? I have a vision language model, and that vision language model can check, did I make a strawberry? And yeah, some different language models, DaVinci, GPT 3.5, GPT-4. Again, GPT-4 might be contaminated with vision, can't say for sure. But the other one, they all do kind of all right. Okay, so these models can succeed here. This unicorn thing that we saw a year ago is not just fake. These models have some competency to do that. Okay. So can language models see? This is a slightly stranger question, but we can actually do the opposite. We can say, not take the language model and make it generate code that renders an image, but take the code that renders the image, which is now a representation of the image in the format the language model can understand, and input that into the language model and ask it, what do you see? Okay, and we didn't want to create kind of a bias and a circularity here. So rather than having the language model generate code that generates images that then get interpreted by the language model, so it's like language model making data that it interprets itself, which might be a little bit suspect, we had humans draw processing scenes. So this is what a bunch of humans on Mechanical Turk did. They would draw simple shapes, and they would draw it in this interface, which was easy to map to the code. So when they draw an oval, we know exactly where the oval is, and we can write the code. Okay, so humans generate images like this. Here are a bunch of examples of that. So, 3 women sitting on a park bench next to each other, and some person on Mechanical Turk thinks it looks like that. So people are pretty good at this too. Language models are a little better, but people are okay at this task too. Okay, I mean, artists obviously could do better, but Mechanical Turk people are okay at this. Okay, now we can ask if the language model that's never seen these images before, because humans made them, can understand what's going on inside those images. Okay, so here's the human drawing of some clouds. We convert it to code, and we prompt the language model as follows. We say, what does the following code represent? We give the code that matches the human generated image, and the language model, sorry, then we make it kind of an easy binary choice for the language model, just in order to be able to assess this cleanly and numerically. And so we say, Is it a lake, a sky, a terrace? Sorry, is it a lake, sky, terrace, traffic lights, or is it a sandy beach? So it's a binary classification task, and the LLM says it's sky. And then that would be counted as correct, and we can measure the accuracy of that system. Okay. Okay, so you're probably expecting me to say it worked beautifully. It actually doesn't. It only works a little bit, but it does work a little bit, and these things are getting better. And so this is a checkup. We can check them again in a year. So here are the different language models that we tried. Already, these are old models. And chance is, it was a 5-way classification task here, so chance is 20%. And in some cases, they're doing a little better than chance. There's even one on GPT 3.5 on recognizing human-drawn scenes converted to code is at 38%. So that's kind of interesting. Okay, but there's a lot of room for improvement. Here are a couple examples of cases where the model got it right. So the human drew the fire hydrant. The model said fire hydrant, right? The human drew the strawberry. The model said it's a strawberry. It's a non-trivial task. Here's somewhere it got it wrong. The humans drew this cake on the top, and the model said it's a beach. But it does look like a beach, right? It's like kind of pink sand and like some flags in the background. This is a humans said it's a chimney or tried to indicate a chimney. The model says it's a sink. These things are pretty hard to discriminate from each other. This terrace was interpreted as a staircase, but I kind of think the model might be slightly more correct than we're giving it credit for, because that does look like a staircase. Okay, so one last thing that we looked at in this paper is we took these images, the images that were drawn by the large language model, so the images the large language model generated the code to draw, and then we tried to pre-train on those images using contrastive learning, using basically the same setup as I showed for the first half of this talk, or the first 2 papers in this talk. So now we're trying to kind of distill all of the visual complexity of the world into a set of language model renderings. So it's like distilling the internet through the language model and then asking it to generate imagery that could potentially train a vision model. And so here's the setup. We train a ResNet 50 on these images using contrastive learning, just self-supervised contrastive learning. We compare that to different methods, and we evaluate on transfer learning now with a nearest neighbor transfer metric instead of a linear transfer metric, and see how well it does as pre-training. Okay, so here's one of these nearest neighbor plots again, just like before. And the lorikeet, if I have a randomly initialized ResNet 50, I get random images. If I use my ResNet 50 trained on these LLM generated images, I get all lorikeets. So it actually works decently well. So just a table making that same point, but I'll just point out that on the bottom rows, we looked at combining the LLM generated data set with the shaders data set, and they're actually complementary. So you get a boost when you put them both together. So to George's question earlier, if you do combine these different processes here, you do get a boost. And the shaders get you about 45% accuracy on this particular ImageNet transfer learning metric, and the language models get about 36. So this random shaders I was showing before are actually quite a bit more effective than these language model generated images, but they are complementary, and combining them can give a boost. Okay, so we're inching that bar up a little bit more here too. Okay. Okay, good. So conclusion. So I'm interested in this n=0 setting. You have no pixels, you have no photos downloaded from the internet, you have other types of data. How can you make use of them? We looked at a few. We saw that you could train from simple equations like maybe fractals or sinusoids. You could train from more complex code that still is describing some mathematical system, but it's I think better thought of as code, as shader code. Or you could train vision systems on data derived from language models. So it kind of raises this question, could you learn to see, could you learn vision from anything, right? And this is something that we've been, it's just a little plug for this hypothesis we put out that we think the answer is yes, roughly, that all of these things are kind of capturing some data about the world out there. Language is an indirect description of visual data. Code shaders are made by humans trying to make compelling artifacts and compelling experiences that are optimized for the human visual system. They're all connected, and we can actually make use of data from more sources for computer vision than you might have thought before. Okay, so I'll end there, and thank you for listening.
Any question?
Yeah, question.
So I'm not very familiar with the object changes. So you have shown this paragraph about the last visual description.
Yeah.
Do you think it emerges this visual explanation sort of seeing because of such descriptions, or in the training set, do we have, I don't know, like some program generates visual scenes and so on?
That's a really great question, and we don't know the data set composition, so we can't address that very easily. I think it'd be good to move to some of the more open models where we have a better idea of what's in the data. My guess is the latter. My guess is most of the ability to generate processing code and recognize images in processing is coming from having seen examples on the internet of processing code. But it's also got to be both. Like it has so much of this both kinds of data, and it's probably some of both. But that would be a really interesting study to try to ablate that. We would just have to spend a lot of money to train new models on that. Yeah.
We have time for one more question. Yep, go ahead.
I just wonder, can you relate these studies with the process of baby learning? I mean, the babies just use a strong way,
Yeah.
just one information learning, and the baby learns it's the same thing. So, do you think there is a relation, or what is the relation? Do you have any comprehension about it?
I think that's fascinating. And yeah, there could be. I think this setting of the active agent in an environment that has to seek its own data could be really related. It's another kind of data set distillation in a sense. Or the general question, I guess, is how can I create the right training data to train my vision system? And a baby rotating a toy around to look at it from all different angles is probably doing that. These are some other ways of doing that. I think there's a lot of connections. Okay. Okay, thank you.
Yeah. Let's thank Dr. Isola once again. So next we have a break for 15 minutes from 10:10 to 10:25. We will come back at 10:25 for the next keynote talk.
La 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 la. La 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 la.
Okay, let's get back to the schedule. Thank you once again for joining us. Our next guest speaker is Dr. Bahalan Mirza Sulaiman. Dr. Mirza Sulaiman is an assistant professor in the computer science department at UCLA, where she leads the Big ML research group. Her research aims to address the sustainability, reliability, and efficiency of machine learning. She's mainly working on improving the big data quality by developing theoretically rigorous methods to select the most beneficial data for efficient and robust learning. She's also interested in improving the models and learning algorithms. The resulting methods are broadly applicable for learning from massive dataset across a wide range of applications such as medical diagnosis and environment sensing. Before joining UCLA, Dr. Mirza Sulaiman was a postdoctoral scholar in computer science at Stanford. She received her PhD in computer science from ETHC. She also received an ETH medal for outstanding doctoral thesis, was selected as a rising star in EECS by MIT, and received an NSF Career Award. Yeah, I think Dr. Mirza Sulaiman is going to present virtually. I think we have her here. So let me mute myself. Yeah, please go ahead, and thank you for joining us once again. Please go ahead.
Thank you so much, Said, for the introduction. Hi, everyone. Sorry that I couldn't be with
Just
you
give me
today
1
in
second.
person.
Is the speaker muted?
I'm not. I'm waiting for Said to fix something.
Okay.
Yes, please go ahead. We are ready.
Okay, thanks. Thank you, Said, for the introduction. Hi, everyone. Sorry that I couldn't be here with you today in person, but I'm hoping that I can meet most of you in the future. So today I want to talk about dataset distillation, but in particular about how we can distill more during the training. So I'm going to talk about this. I'm going to explain this more shortly. So as an introduction, we all know that data is the fuel for our machine learning tasks. And for example, if we look at this example of object detection from Google AI, we can see that as we increase the number of examples on the x-axis from 10 million all the way up to 300 million, we get this logarithmic improvement in the performance of object detection task. Y-axis is in log scale. So this clearly shows that large data and data in general is very important for machine learning. But the issue is that training on big data is very expensive usually in terms of memory, computation time, and also costs. And because of all these constraints that in a lot of applications, we are usually limited in terms of resources if we think of, for example, edge devices. For a lot of times, we want to train a model several times over and over, for example, neural architecture search. Or another use case is that a lot of times we want to preserve the privacy of the training examples. And as we all know, these days, there are a lot of techniques that people can figure out information exactly about the training data, who was in the training data or not, or they can discover training examples by just querying the model. And because of all these motivations, it would be nice if we can have kind of a smaller distilled version of a big data, such that we can quickly train a model with it. And we can repeat this, we can have this, we can do this on edge devices, we can repeat this many times, and we can also preserve the privacy of the training data. So one of the very nice existing solutions these days is dataset distillation. So as many of you may know, the way dataset distillation works is that we want to synthesize and generate a small synthetic subset of images such that when we train a given model on the actual potentially large training data, and this smaller synthetically generated data set, the performance of the model trained on the full data, and this is a smaller subset, is almost the same. And usually we are interested in generating a smaller subsets due to all the limitations that I just explained. So for example, we want to generate 5, 10, or 20 image per class, which we call it IPC. And we want the performance of this smaller synthetic subset to be as close as possible to the performance of the model trained on full data. And if we can do this, then it greatly reduces the memory requirement of storing large data sets, large financial and environmental costs of training on large data sets. It can speed up a lot of applications such as neural architecture search, continual learning, and it can preserve the privacy of the training examples very well. So in fact, dataset distillation is more successful in preserving the privacy of training data than a lot of other privacy-specific proposals. Okay, so here is an example. As you can see, this smaller distilled set of examples, they are not exactly looking like real images, but they look like compact version of examples in different classes. Okay, so there are different ways, there are different proposals for dataset distillation these days. Two of these proposals that are particularly relevant for the talk, for this topic that I want to talk about today, is generating data by matching the weights or parameters of the network being trained on real data during training, or matching the gradients of the network being trained on the full data during the training. So there are other ways, but these two proposals in particular, they are trying to capture the training dynamics of a model being trained on a real data set. And so the goal is to generate a smaller synthetic data such that when we train a model on this smaller data, the network weights or the gradients of those parameters are very similar to the network parameters or the gradients of a model trained on the actual big data. So if we can achieve this, then we are making sure that the network has similar training dynamics and the network converges to the same solution as that of training on the full data. And this ensures that we are getting a very good performance or similar performance to that of training on the full data. Okay, so let's look at the first one a little bit more closely, training and matching the training trajectories or matching the parameters or weights of the network. So the way this proposal or MTT works is that we are having a teacher model that is the actual model trained on the full real data. And this blue trajectory of weights are the trajectory of the weights of this network that we are training on the full big data. Now we have, we want to train this model. We want to find a smaller synthetic subset of synthetic set of examples, such that when we train the same network on it from the same initialization, these orange generated trajectories, they converge to the same point as the blue. So we are generating these examples by minimizing a loss, which is defined as the difference between the orange weights and the blue weights. So if we can minimize this loss, we can generate synthetic examples by minimizing this loss. We are making sure that the training on blue real data and training on orange synthetic data, they are converging to the same set of parameters. So we are training the same model, finding the same solution, and we get a similar performance. So as you can see, minimizing this loss requires back propagating through this, the updates, all the updates of the student network. And it requires a large kind of memory. It needs a large memory, it has a large memory requirement. And as a result, we cannot distill long, very long training trajectories with it. And it's a little difficult to generate a lot of synthetic examples because of this limitation. So we can only match smaller training trajectories of the blue, and we can only generate a limited number of examples. Okay, let's look at the other proposal, gradient matching. So another set of dataset distillation methods generate synthetic data by matching the gradient of a network being trained on the full data, for example, right? And they are generating a synthetic set of synthetic examples that have a similar gradient. Again, the motivation is that if the gradients are similar, the parameter updates are going to be similar to parameter updates of training on the full data. And as a result, these two models have a similar training dynamics or training trajectory, and the solution will have a similar performance. This proposal is even more expensive in terms of computation time and memory, usually, than MTT. So with both of them, we can only match a small part of training, either in the weight space or in the gradient space. And we cannot generate a lot of examples or a large value for IPC. Okay, and if we look at the performance, for example, for MTT with IPC10, similar for IDC, there is usually a gap between the performance of these methods compared to the performance of the network trained on the full data. And here I'm showing 3 different data sets, CIFAR10, CIFAR100, Tiny ImageNet. And as you see, CIFAR10 is the easier data set. It's easier to do well on it. CIFAR100 is a little more difficult, and Tiny ImageNet is the most difficult. And you can see that the gap increases. The gap of training on distilled set versus the gap of training on the actual full real data. So the question is that why is this the case? Can we kind of know, is this only the error of dataset distillation, or there are other reasons for it? So we were looking at this question, and something that is interesting, like just to make it more concrete, MTT can distill only the first 15 epochs of a 200 epoch training pipeline of CIFAR10 or CIFAR100. And IDC, which is one of the state-of-the-art gradient matching techniques, can only distill the first 4 epochs of the full training trajectory, right? So this is kind of showing that we are not really distilling the long training dynamics that we should probably be matching. We are only distilling the very, very first part of the training. And this is actually one of the main reasons that we have a gap in the performance of this training on distilled data and training on the full real data. But why is it? Like, why distilling the first part of the training is not enough? So if we look at the training dynamics, so at the very beginning of the training, we are learning simplest examples, like easiest examples. You can think of the most obvious cats or dogs or different objects. We are learning those examples. We do well. We can classify them correctly. After that, we are learning a little bit more complicated images, like a little bit more vague dogs or cats or objects. And at the end of training, there are some images that even us humans, when we look at them, we don't know what is the class. The model is going to overfit those. So technically, we are learning based on the level of simplicity or difficulty of learning. The simplest examples we learn first, and this is when we train on the actual full data, not this still set. This is kind of the training dynamic. Now you can imagine that if we only match the training dynamics of the very first part of the training, then the images that we generate, the synthetic images that we generate, are going to be representative of the simplest and most obvious examples in the data. And if the data set is easier, like CIFAR10, we are going to get a smaller gap to training on full data because more examples are easy and we are matching more examples. But if the data set is more difficult, like CIFAR10 or in particular Tiny ImageNet, then matching the very first part of the training is not enough because the number of simple examples in these data sets are a lot smaller. And then we can only do well on those very simple examples when we train on the distilled data. Okay, so to kind of give a little bit more context on why this is the case. So there are a lot of recent theoretical and also empirical studies showing that this happens, like this learning in order of the difficulty of examples. We are learning in this way because of the simplicity bias of gradient descent. Like gradient methods in general, and one of the gradient methods is the stochastic gradient descent that we are normally using, or Adam or other gradient methods. They are all having this inductive bias towards learning simpler functions, in particular early in training. So what does it mean? It means that if there are multiple solutions, all with the zero training loss, SGD is going to find the simplest one, for example, the smallest norm solution, right? And the way that SGD is learning is that it is first learning a linear model very early in training, first few epochs, then second order, third order, higher complexity models during the training. And very high complexity models in the end are going to overfit those examples that we cannot distinguish by looking at them, right? So because of these reasons, we are learning functions of different complexity, like higher complexity during the training. Now you can see that if we only distill the very first part of the training and generate examples based on that, then we are going to kind of be able, by training a model on this distilled example, we can only learn a linear function or very simple function like second order or third order, right? We cannot really train a model that can capture very complex functions. And this is the reason that we see this gap, increasing gap, when the data sets become more and more difficult. So let me show you some of the kind of results from other works that people have shown, not on dataset distillation, but on what examples are, for example, we can drop from the data, or what examples are most important for supervised learning in general. And then I want to connect this to what we should do or what we are doing for dataset distillation. So in general, people have shown that difficult to learn examples benefit supervised learning the most. So what does it mean, or what is even the learning difficulty? Like intuitively, we know what is difficult, what is easy, but let's make this more concrete. So one of the most intuitive scores to capture the difficulty of example is forgetting score. Forgetting score says that train a network on a data set and count during the training how many times prediction of an example switches from right to wrong. Right, for example, we have a 200 training pipeline for CFAR, 100 or 10. Then for every example, we keep a counter and we increment that counter if the model is classifying this dog correctly, and now next epoch, it's flipped to wrong prediction. And now if you look at the left plot, so this paper shows that you can safely drop the easiest examples with forgetting score of 0 or small forgetting scores, those examples that network learns quickly. You can drop them from the data and you lose nothing in terms of accuracy. So y-axis shows the test accuracy, x-axis shows the percentage of training data that you can drop, and this is CFAR 10. So red is full data, training on the full data, and green shows what happens if we drop different percentage of examples that are easy and have a very small forgetting score. You see that the easiest examples you can drop and you lose nothing, right? So now you can look at the right plot. So right plot is another paper, is one of our works that are showing that if we want to do data selection during the training, the best selection strategy is selecting the smaller forgetting scores early in training, but then selecting examples with higher forgetting scores, more increasing level of difficulty during the training. So again, we see that it is very important and most important to train a lot on the more difficult examples, not the easier examples that are learned at the very beginning of the training. So this kind of motivates that we shouldn't limit ourselves to the very first part of the training if we really want to bridge this gap to training on the full data. But we should really be able to distill more of training dynamics, like later after epoch 15 or after epoch 4, right? Okay, but how can we do this? Because dataset distillation in general is very computationally and memory-wise very heavy. So just by increasing the length of the training trajectory that we match, we cannot do better. It becomes just computationally prohibitive to just increase the length of the training trajectory that we match. So just going back and make it a little bit kind of highlighting it again. So what we want to do is that currently we are generating based on the very first part of the training. What we want to do is that we want to also capture the middle part, a little bit more complex functions. And we want to be able to generate synthetic data based on not only the first part, but first and second part, let's say. Okay. So, and as I was mentioning, this is impractical and prohibitive just to increase the length of the trajectories that we match. As a result, we were thinking of how we can address this, how we can distill a little bit more. And our proposal was that let's generate multiple synthetic subsets, multiple smaller synthetic subsets, one for the first part, one for the second part, one for the third part. And if we can do this, then when we want to train the model on the synthetic examples, we can first training on the first subset, then on the second subset, then on the third subset, so on and so forth. And now we can use most of the existing dataset distillation methods to kind of distill these smaller subsets by capturing different parts of the training dynamic. Okay, so what we want to do is that we want to generate this small subset S1 for part 1, S2 for part 2, S3 for part 3, so on and so forth. And now this is tractable because each of them are very small, and we can use most of the existing dataset distillation methods. Okay, so key takeaway so far is that distilling one subset is not enough, at least for now with existing methods. But what we can do is that we distill multiple small synthetic subsets during the training. So during the distillation time, each synthetic subset captures the training data, training dynamics of training on full data in a different part at different time or different interval during the training. And at test time, when we want to train the model on the synthetic data, we can train on different synthetic subsets one by one. So still memory-wise and computation-wise, it's gonna be fast. Okay, but naively, just capturing different parts of the training doesn't work well. So reason one is that if we generate different synthetic subsets that are independent of each other, then we may capture a lot of redundant informations. We cannot really say that, okay, phase 1 is 2 epochs, phase 2 is 2 epochs. It's not clear like what is phase 1, what is phase 2. So if we just divide and generate for different intervals of training, we are going to naturally capture a lot of redundant information, which we don't want to. It's not optimal. And the second point is that, so during the test time, when we want to train a model on different subsets, imagine that I have already trained on subset 1, now I'm going to train on subset 2. If I train a lot on subset 2, which is usually the case when we are training on the distilled subsets, subset 1 is forgotten by the network, maybe forgotten by, like the network may forget the past, right? Now I'm training on subset 3, the network may forget subset. And we have to be careful about these 2 points. So how can we address this and still making sure that we are generating high quality and meaningful synthetic subsets during the training. So for the first point that we don't want to generate independently, what we can do is that, first of all, like we can generate subset 1 the same as what we are doing, so like for the existing methods. But when we want to generate subset 2, first we are training the model on subset 1. Now we are generating subset 2 conditional subset 1. Like we add subset 1 to the set of distilled examples. And now we are generating subset 2 such that union of subset 1 and subset 2 captures the gradient or the weight trajectory of phase 2. Right. Okay. So again, we are generating subset 1, but when we want to generate subset 2, we want to make sure that the union of subset 1, which is fixed when we want to generate subset 2, and the subset 2 that we are generating, both of them together capture the training dynamics of phase 2. And now when we want to generate subset 3, we want to make sure union of these 3 subsets, subset 1 and 2 is fixed. We are only generating subset 3, but we want to make sure that the union of these 3 subsets match training dynamics of phase 3. And if we do this, then we are making sure that these subsets are not independent anymore, and they are not redundant anymore with respect to each other. Okay, now, how do we make sure that the network doesn't forget the past? So what we can do is that, as I mentioned briefly, so imagine we are generating subset 3. When we generate subset 3, we train the model on subset 1 and 2. And we are generating subset 3 that matches training dynamics of full data, but starting from this theta 2, which is the model weights that is trained already on subset 1 and 2. So we are matching from this point, not from the initialization. Right, so instead of matching everything from initialization, we train the model on the previous subsets. And now we are matching the full data starting from this trained network. This way, let us ensuring that the information is preserved in the model and we are not going to forget it. And also remember that during the test time, as I'm going to explain further, we first train on subset 1, then we train on subset 1 and 2, then we train on subset 1, 2, and 3, then 1, 2, 3, and 4. This further ensures that we are not forgetting the past. Okay, so to sum up, the key idea was that we call this progressive data distillation, PDD, to generate multiple smaller synthetic subsets by matching the training dynamics at different stages or different intervals. Okay, so if we look at this visualization, I'm not sure that you see my cursor or not, but we first generate S1 for the very first part of training. We train on it to get theta 1. Then we add S1 to the subset. We generate S2. Given S1 is there and is fixed, we only generate S2 by matching the dynamics of network being trained from theta 1 on full real data. And we keep doing this as many times as we want, and we get multiple smaller synthetic subsets. And at test time, when we want to train on them, we train on S1, then S1 and S2, then S1, S2, and S3, and so on and so forth. Okay. Now, can we further improve the efficiency of this pipeline, right? So we can. So if you remember, I was saying that network in general, models, when being trained on a real data set, first learn easy examples, then a little bit more difficult, then a little bit more difficult. So what we can do is that we know that when we generate S1, this is representative of the simplest example in the data. Now for the second stage, we can get rid of all these easy examples in the real data, and we can distill the rest. Now, when we generate S3, we can discard more of easy examples, and we can only focus distilling the rest. And this should work faster, but very similar to distilling everything every time. Okay, the reason is that at the second part, network already learned the simple examples, and they are not affecting the weight trajectory or the gradients anymore anyways. So if we discard them, we are not losing anything. Okay. So at every distillation step, we just drop more of simple examples such that we can only focus on distilling the more and more difficult examples. And this improves the efficiency without harming the performance. Okay, let's look at some experiments. So here are different baselines, different IPCs in different columns, CIFAR10, CIFAR100, Tiny ImageNet, IPC 1050. And baselines, data selection baselines, random herding, K-center for getting the scores, and some distillation baselines, DC, DCA, are gradient matching ones, DM is distribution matching, which is not using the training dynamics. MTT is the weight matching one, and IDC is the gradient matching one. So you see that adding PDD, multiple stages, to MTT and IDC, this is improving the performance by up to 4.5%, which is nice. And it also allows us, for example, in the case of Tiny ImageNet, we can easily distill and generate many more synthetic examples, which is prohibitive with most of current dataset distillation pipelines because of the very high cost of training more, of generating more distilled examples. So here, because we are generating multiple small ones, we can just keep doing this as many times as we want. This is also a nice property. Okay, so this generated examples with PDD, when combined with other methods like IDC or MTT, they are also generalizing well to other models. Usually we are distilling based on a smaller network and we want to train a much larger network. So this is also nice, a good sanity checking. And now let's see if we can help bridging the gap. So you see that for CIFAR10, CIFAR100, and Tiny ImageNet, IPC10 and IPC50. So as we increase the number of stages, we can actually bridge the gap more and more for all of these data sets. In particular, for CIFAR100, we can almost close the gap to training on the full data. And as we increase the number of stages, we are doing better and better. Now, this is for training on the synthetic examples. So P is what I was explaining, like train first on S1, then S1 on S2, then S1, S2, S3, and so on and so forth. S is just training on S1 first, just training on S2 first, just training on S3 first. And U is training on everything together. And you see that P, which is S1 first, S1 and S2, S1, S2, and S3, like progressive, adding these smaller distilled examples, this is doing much better than the others, in particular, when we are increasing the number of stages P. Like when we are generating more, in particular, P is doing much better. Okay, so a little bit more results, like left table shows the importance of transitioning and conditioning. Conditioning is when we want to generate S2, we generate it assuming that S1 is already there, right? We don't change S1, but we put S1 and condition on S1 that generate S2. You see that this is helping actually. And transitioning is that when we want to generate S2, we first train the model on S1 and we generate S2 by matching the full data, but starting from the model trained on S1. So both of them are helping the performance and they are important for getting a good performance. So now let's look at the right table. For right table, we are looking at, like, if we want to generate a fixed number of synthetic examples, for example, 10, IPC 10, is that better if we generate at one stage or 10 examples, 2 stage, 5 examples each, 5 stages, 2 example each, or 10 stages, 1 example each with the same method. And you see that more stages generally helping, like 5 stages each time generating 2 is best. In general, more stages is better, but when we are generating very, very small, like 1 example per stage, that is usually not helpful. So in general, increasing helps as long as what we generate is not super small, like 1 example. Okay, so here there is some other results on the improving the efficiency of PDD, meaning that at every stage, we are first discarding the simpler examples, more of simple examples, again, based on the forgetting score, we did this, but we can do based on other metrics of difficulty as well, shouldn't make a difference. But here, for example, for the first stage, we are distilling everything. For the second stage, we are discarding all the examples that have a forgetting score of less than 3. Then in the third stage, we are discarding all the examples that have a forgetting score of less than 6. This is just what we did. It may not be super optimal, but you see that we are getting a very, very similar performance to that of matching the full data for each stage of PDD, but this is much faster, which is good. Okay, so another experiments that we have here is just another application of dataset distillation, continual learning. This experiment is for CFAR 100 across 5 phases. In each phase, we only have 20 classes. This is how continual learning works. At different times, you can only see part of the data, some of the classes of the data. And in this setting, we can only access 20 classes, and we are generating 20 images per class. And during the evaluation, we are training sequentially on samples available at each stage. So here, again, you see that when we combine PDD with, for example, MTT, the performance is improving a lot, relatively. Okay, so last slide. If we look at what are the examples that we generate at different stages and how do they look like, you see that at the very beginning, we are capturing a lot of colors, right, at the stage 1. At the stage 2 and 3, we are capturing more of high-level contours and those kind of shapes of the objects. In the stage 4 and 5, we are focusing more on the texture. So it seems that we are going from color to structure to texture somehow. And this is kind of similar to the way that models learn things during the training from a full data set as well. So it seems that we are somehow PDD is relatively successful in capturing different training dynamics during the training. So this was what I wanted to talk about. The rest of it, I'm hoping that there are some questions and we can talk a little bit about things. Thank you so much for listening. Not sure if there is any question or anything I can explain further.
But this.
Okay, thank you for sharing work. So in your paper, you mentioned that you split the training stage into different stages because they learn different information. So have you tried to like match multiple stage at one internal loop, like quantile?
I do not hear you very well. I'm not sure if there is a way, if somebody can repeat the question for me, please.
You can come here and answer your question.
That would be great.
Okay, thank you for the inspiring talk. So, in your paper, you split the training stage into multiple stages because during the training, different stages learns different informations, right?
Yep.
So, have you tried like matching the trajectories for like for multiple stage in one in internal loop. Yeah.
So you mean in one stage we distill more longer trajectories?
Yeah.
So you cannot do it because of computational reasons. Like for example, I was showing that for MTT, the default is distilling 15 epochs, and for IDC, the default is distilling the first 4 epochs. So we played with these numbers a lot, and it appears that these numbers are actually optimized. Like you cannot, like if you go smaller or larger, you cannot do better. You are losing performance. So when you go larger, you are trying technically to produce examples based on longer trajectories, but because of computational reasons, you cannot reduce the distillation loss a lot. Like you are not doing a good job in producing those examples because the problem becomes very complicated to solve and you cannot solve it well.
Okay, thank you. And
Sure.
the second question is, the framework you propose is very interesting. Could it be used to the transfer learning models? Like the model first train on one data set and maybe fine tune on another data set, and we want to distribute the model from the second data set because the training stage is different. So can we apply
Yes,
your
that's a very good question. I think it is doable, and I expect it to work maybe even better than training from scratch. The reason is that for transfer learning, usually the fine-tuning time or the number of epochs for fine-tuning is usually smaller than training from scratch. And that's why we are having perhaps a smaller number of stages. And it would be easier, for example, you need to distill a smaller amount of time, fewer times. For example, instead of doing it 5 times or 6 times, you can do it 3 times and you are already doing good. So that's my expectation. We didn't try, but I think it should work. The only point is that you have to, instead of distilling from random initialization, I think you have to start from the pre-trained network weights, and we have to steal from there, like matching trajectories by training from that parameters.
Okay, thank you.
Sure. Thanks for the questions.
Thank you, Dr. Mirza Suleiman, for your talk. Let's thank Dr. Mirza Suleiman once again.
Thanks. Thank you so much. Hope to see you guys very soon.
Yeah, thank
Bye.
you. Okay, let's move to the next keynote talks given by Dr. Flying Huang. A brief introduction to her would be Dr. Huang is an assistant professor of the Department of Computer Science at the University of Maryland. She works on statistical and trustworthy machine learning, reinforcement learning, robustness, and fairness. Dr. Huang is a recipient of the MIT Technology Review Innovator under 35 Asia Pacific Award, the MLConf Industry Impact Research Award, the NSF CRII Award, the Adolph Faculty Research Award, the JP Morgan Faculty Research Award, and finalist of AI in Research. AI Researcher of the Year for Women in AI Award North America. She received her PhD in electrical engineering and computer science from UC Irvine in 2016, after which she spent 1 year as a postdoctoral researcher at Microsoft Research, New York. Yeah, let's invite Dr. Huang.
Go. Right. I think there might be a problem.
That's, yeah, that should be unmuted. Yeah, good. What's that?
There seems to be a.
Are you sure? Are you sure?
Looks like it's not.
Page in your slide. Go to the next page. I think that should work. Yeah, that should be fine, right? If you go to the next slide now, it doesn't go. Just let's click here. Yeah, that should work.
Okay, just want to make sure for people on Zoom, you're seeing the full screen, right?
We should be all fine. Should be fine.
Okay. All right. Think people can hear me or no?
Yes, I think so.
Okay.
Get a little bit closer.
All right. Thanks. So hi, everyone. I'm Farong. I'm assistant professor from University of Maryland. And today I'm going to talk about advancing AI with data-centric strategies. Specifically, I'll talk about efficiency, generalization, and trust. So we know data is really important, right? So there is this interplay between the data and the model. You can use the data to train your model, but at the same time, you could also use the model that you've trained to generate data. So, however, there are a lot of problems, although despite the very important role of data. First of all, data are not really efficiently used when it comes to training models. For example, in this figure I'm showing here, Llama 2 was trained on 1.4 trillion tokens, which is 3,800 times more than a human would have verbally exchanged at the age of 50. But you would still argue, what is the efficiency in terms of data, right? And if you look at this picture here, this is the training loss versus the billions of tokens that a Llama model has trained. Well, actually 4 Llama models trained. You would sort of see this kind of saturation of this training loss at some point when you increase the tokens, which suggests that data are not really efficiently used. So that's why we're here gathering to talk about data distillation, which is basically learning to compress. Can you compress your data in a way so that it renders efficient learning, right? So on the other hand, I was talking about this interplay between data and model. Your model is really getting bigger and bigger, right? So as you can see here, nobody is going to argue with me that models are really getting bigger and bigger. And some papers even brag about the models being the biggest. Well, on the same time, when the model is getting bigger, also means, based on very principled arguments in AI and ML, do you have this data you need to train these bigger and bigger models, right? So in other words, will we ever run out of data? Here is a picture showing that it is predicted to happen during 2023 and 2027. Actually, we're 2024 now. Is it really happening? Here is something I wanted to show you. So you have this recent large language models, GPT-4 trained on 6.5 trillion tokens, Llama 3. Let's use Llama 3 as baseline, okay? So that's one Llama. And GPT-4 is half a llama. Now, if you think about the private data, it seems like we still have a lot of data, right? So, you have all these internet messages, you have all these stored emails. There were like 45 llamas and 80 llamas. However, unfortunately, you cannot really use them, because they're private and you run into these copyright issues and privacy issues. Well, what about web scale, like open source data? Yes, you can see fine web and non-English web data, they're exactly at the borderline of 1 llama now. So what really means here is we are actually running out of data, and it's happening right now. The prediction was kind of right because, set a range, and today is 2024. So with that, I wanted to also talk about learning to generate. There's this kind of weird contrast, right? So you have this very low efficiency in terms of using your data. You want to compress your data to improve your efficiency. But on the other hand, your model is getting bigger. You need more data. So we also need to generate high quality data to help you get rid of this overfitting issue, right? So I'm going to talk about both. But also, at the end, I also wanted to mention that a lot of the hypes about AI ML really right now may come from that we're not benchmarking or we're not evaluating correctly because there's data contamination. There's the question of where there always be unseen data for benchmarking. Actually, you see this very impressive results. You see that all the time on the internet. AGI is coming. Superhuman level models are coming. But are the real reasoning abilities really getting closer to human? And that's the question I wanted to ask. And there is a very interesting paper showing that indeed your benchmarking data is very likely a mixture of training and test. So there is data contamination. And if you get rid of this kind of training data, your evaluation would drop drastically. Not surprising. So in this talk, I wanted to sort of talk about the trust issues, right? In terms of evaluation, but also in terms of the safety issues in AI. So I would ask this question, do you trust AI? Unfortunately, only 39% of US adults would say that they believe that today's AI technology are safe and secure, which is unfortunate. Although, almost 80, 60 something, I don't exactly remember the number, 60 something number of, the applications and deployments and softwares are actually run by AI nowadays. So aligning AI with humans are extremely important. And indeed, all these government entities realize, and then they put the executive orders and stuff like that to emphasize, to make sure that researchers in the field working on this very important trustworthy issues. So as a result, I'll be talking about 3 things, covering, some of the recent work in my lab doing, in terms of learning to compress, learning to generate, and boost trust. So let's get started. Well, learning to compress is sort of the central theme of this workshop. And a lot of you, previous speakers have given you very good coverage of, what you need to do to understand data distillation. But here, I sort of wanted to talk about a slightly unique perspective, which is, you would think that standard data condensation has already been covered in this workshop so far, would find a small synthetic, training set so that the test performance on the model trained on the original training set versus the synthetic training set is comparable. Well, however, there is a problem, right? So, the advocate for this approach is to improve efficiency so that during training, you don't have to train on this gigantic data set, you could train on a small data set. But unfortunately, during training, you never do it once. You have to do so many times, you have to do hyperparameter tuning, you have to find a better model, you have to, maybe tweak your learning rate and stuff like that. So how do you deal with it? Is there a problem with it? Indeed. So if you consider this kind of hyperparameters, it generates really poorly across different hyperparameters when you do this kind of data condensation or data distillation. So how to solve it? We just propose a simple idea. We call it hyperparameter calibrated data set condensation, which is a new condensation objective that's specifically geared towards this hyperparameter search. So the idea is pretty simple. So what we did is basically define a validation set. So on top, you would have like the original validation set. Down here, you have the synthetic validation set. So you want to find a small validation set such that the validation performance ranking of the model with different hyperparameters on the synthetic versus the original are comparable. So how do we do it? You could do the evaluation here, for example, using this models trained from the original training data, and you can evaluate on this original validation data, right? So you get a loss. And on the other hand, you could just do the same thing, but both on the synthetic training and the synthetic validation data set. And in order to make it comparable, you can notice that both of these are going to be a function of lambda, lambda being the hyperparameter. So it varies as lambda varies as well, right? So you wanted to make them comparable. So all you need to do is matching, and we've talked about it many times in this workshop so far, okay? So, but there is a caveat here, though. Matching seems to be easy, but it's not because it's a function of lambda, and lambda is not necessarily directly differentiable. Okay, so we did a bunch of tricks. For example, we learned synthetic validation set to match the hyperparameter gradient of the validation loss with respect to the hyperparameter. Actually, it becomes a bi-level optimization problem with all the details I'm not going to talk about for the interest of time. So at the end, the loss is going to be a hypergradient match loss, which involves some kind of implicit gradient calculation of this lambda here. Anyways, so at the end of the day, we propose that when you talk about data distillation, you should think about validation. You should not only do that for the sake of the training set. You should also do that for the validation set. And we update the synthetic validation to minimize this kind of gradient matching loss. Okay, so here are some results. Basically, I know there is a lot of information here, but all you need to take away is that there is a high correlation after you do this kind of HCDC mechanism. You will see a better kind of performance preserving when you vary your hyperparameter. So this will be really helpful when you do a hyperparameter search during your training, and you can do this using a very small data set. Okay, so that is what I wanted to talk about in terms of learning to compress. As I motivated earlier, we also wanted to care about whether we run out of data. In some regimes, we're in the big data regime. In some region, we're in the small data regime. So I'll talk about some recent work we're doing, which is learning to generate. So the classic data generation, everybody knows, is augmentation. And indeed, augmentation is probably one of the most important techniques that make computer vision so successful, right? We know how to do, data augmentation for natural images, and I don't think I need to talk too much about this in this audience. But does it really work for all kinds of images? What about medical images, right? And it's not very surprising. On medical imaging, you see performance decreases. Also on tabular data and graph data. So anything that is not natural image, you see some kind of performance degradation, unfortunately, using just the augmentation that we're doing on natural images. So how do we fix this problem? First, I wanted to ask the question, why does it not work? Right, so not very surprisingly, augmentation heuristics sometimes just does not make sense at all on this kind of medical images, right? So imagine we can see two types of errors. There is this impossible data that is just the morphology of your tissue shouldn't exist, right? So when you do this kind of transformation on your image, biologically, it shouldn't exist. It's just impossible, right? So that kind of data augmentation is basically useless and some, even worse, misleading. Could also imagine this kind of wrong labeling, which means that, I am doing this kind of augmentation, and originally it was a cancerous tissue. And after doing some augmentation, it no longer become a cancerous tissue, but I still label it as cancerous tissue. So that's, again, misleading. So what should we do? How do we fix it? A very easy fix, you imagine, to have a reviewer, right? Very natural thinking. We just need a reviewer for augmentations. And how do we do that? It's just like acting between like data augmentation and the model training. You just have a reviewer, maybe an expert, right? Because we need domain experts, especially for medical images. But experts are so expensive. We really wanted to have an automated pipeline. How do we do that? So that's our work. We call it SafeFlex. It is a really kind of versatile method that works with any upstream data augmentation, acts as an automated pipeline to fix your augmentation when they were wrong. So how do we do this? Very simple. Starting from XY, which is your raw data with label Y, you do some kind of augmentation, whatever, your favorite augmentation, you'll get XAug and YAug, and then SafeFlex is going to say, hey, I'm not necessarily going to have a fixed sample weight. I'm going to learn the sample weight of this augmentation in the case that this augmentation shouldn't really be feasible. And I'm also going to learn a soft label in the case that the augmentation would change this data point from one side of the distant boundary to the other side. So this is basically what SafeFlex does. And it works like a domain expert with like dropping and relabeling of their data, right? So if it's impossible, I'll just drop it. If it is wrong label, I'll just relabel it. What SafeFlex does is basically a soft version of it. So, I don't drop the label. I don't drop the sample. I could just, learn a sample weight, right? That is not necessarily 1. I could even increase the sample weight to be greater than 1. Or I could also learn a k-dimensional data class label. So learn this kind of soft label rather than the hard label. So that's what SafeFlex does. It turns out it works really well. But before that, there is a mathematical thing that I wanted to tell you, which is how do we learn these kind of sample weights and soft label? What kind of objective you want to learn that? And it turns out we argue that you have to learn these things based on the goal that you want the resulting model to perform really well on the validation data. So again, I'm resonating to the previous project here that the performance on the validation data is really important. So if that happens, then you need to evaluate your model on the validation data, and then you're going to design your objectives so that your validation performance is maximized. And it turns out this becomes, again, a bi-level optimization problem that you have an outer loop optimization that is trying to optimize your model parameters as well as your data augmentation, which in this case is just learning the WAug and the YAug. And then in the inner loop, you want to find the model that is the best based on this data augmentation. And this interplay really gives you very good results overall. As you can see here, we tested a medical images, tabular data and diffusion model generated augmentations. And it even works for contrastive fine-tuning. Here, I'm just showing you a few results. For example, on this medical images, you can see performance increase compared with prior state of art, for example, RAN-AUG. We also tested on tabular data. As you can see, also results are pretty promising, I would say. So now I talked about learning to compress, learning to generate. How about boost trust, right? As I motivated that there is a lot of problems in terms of evaluation, and we believe we're in a data-centric AI. So my group has been working on, trying to understand how to evaluate these state-of-the-art models, especially when it comes to like a multimodality, right, in these large language models. So we built a few benchmarks to understand how to test the real limits of these models. So the first one, I'll show you a kind of a very simple sequence of images. So this is the first image you would see. And then you see second image, third, and fourth, and that's it. So it seems to be a very simple series of images, right? A sequence of image. And it's a really simple scene. I think nobody will be like confused about what may be happening in this scene. Indeed, if you ask a human annotator, they would just tell you, hey, the sequence of image depicts 3 men interacting on an outdoor staircase, and the man in brown is ascending the stairs and blah, blah, blah. Okay, so it's really normal. I think nobody will miss it. However, if you ask the state-of-the-art large language model, or actual vision language model, write a description for this given sequence, image sequence in a single paragraph, what is happening in this episode, you would imagine it will describe something, because it's so simple, right, to human. But unfortunately, there will be a lot of hallucination in this description when it comes to a sequence of images. And it's basically, you would have the large language model would not recognize there are 3 men in total rather than 2, because they didn't see the men, hiding in the door. And they would actually think that this thing here, if you can see my cursor, this seems to be a weapon rather than just the hand railing, which is quite interesting. Actually, if you look at it, it kind of looks like that. But anyways, so you see, basically, vision language models seem to be really bad in terms of doing like a sequence image reasoning. This is for daily life domain, and we actually also did it for robotics as well as cartoon. Actually, GPT-4 is really bad at reading cartoon animations, which is very surprising to me. Anyways, so we did this work. We call it Mementos. It is a comprehensive benchmark for multi-model, large language model reasoning over image sequences. And it's really designed on the 3 domains, daily life, robotics, and comics. And we're trying to test the limits of vision language model when it comes to reasoning on this image sequence. And you can see some statistics about this data, for example, episode length, for example, image sequence length. So we try to make it as comprehensive as possible. So, if you're curious about how models perform on this benchmark, they don't perform very well, as you can imagine, right? So it seems like to be a really challenging task for the existing state-of-the-art models still. Okay, but you may ask me this may be difficult, right? So, but you say this is difficult, but how do I know something is difficult? Or how do I know these models are able to learn, easier things better, or, more difficult things better? How do we quantify that? So with that question, that's why we built another benchmark. We call it easy to hard bench, which is a standardized difficulty labels for profiling large language model performance and generalization. So the idea is pretty simple. We wanted to understand how models are performing based on different difficulty levels of this data. And we don't find a data set that really has a continuous and a standardized difficulty label, especially in the domain of code, math, and chess, which requires a lot of reasoning. Okay, so that's what we did. We wanted to build such a benchmark so that we could really test the limit in terms of whether the models are performing better in easy or hard. So we did this, and here is a few statistics about it. And if you wanted to, you're curious about the performance, it turns out that not very surprising, these large language models really cannot perform very well when it comes to code. and AMC, which is math. Well, they perform a little bit better when the tasks are simpler, but they really fall short when the tasks becomes more difficult. And also very interesting, wanting to understand this kind of easy to hard generalization to test the limit of whether you learn from easy questions, whether you're able to somehow generalize to understand harder questions. So we did this on the x-axis, you have the evaluation difficulty. On the y-axis, you have a training difficulty. So you train on specific difficulty and evaluate on specific difficulty. And you can see it's actually quite interesting that this kind of easy to hard generalization may be possible. I just wanted to say maybe. I don't have a very concrete conclusion yet. So I think it's a very interesting problem to study on with this benchmark out there. Okay, so finally, very quickly. Yeah, so here I've talked about, here I've talked about a few benchmarks here, but I also wanted to talk about trust, as I'm motivated here that a lot of the trust about the large language model, I think is really attributed to that we don't have enough data or essentially red teaming to generate edge cases to test the limits of these models. So for example, everybody knows deepfake, right? Deepfake is a terrible kind of situation we all want to defend against. So there is the question of whether the content is AI generated or is real, or if it is AI generated, which platform generated it, or even specifically which user actually generated and spread it. So we wanted to answer these questions, not only for text, but also for images or even videos, right? So that's why we've been trying to understand the detectability of this AI generated content, first from the text perspective, just pure text. So we had this paper earlier this year on the possibilities of AI generated text detection. And actually very different from the very pessimistic views that is very popular in the community. We say that there's always a possibility to detect these AI generated content, but with a caveat of you observe more or you observe longer text sequences. So here, we're basically trying to test the RUE-AU-ROC curve, the area under the receiver operating characteristic. It's a performance that you can use to evaluate the classification models, right? So basically an AU-ROC of 0.5 means that is a random coin flip, right? So the performance is basically a useless model. And an AU-ROC less than 0.7 is suboptimal, but maybe 0.7 to 0.8 is a good performance. AU-ROC greater than 0.8 is excellent. AU-ROC 1 is basically like perfect classifier. So based on this, our result is like this. So first, the AU-ROC. Oh, yeah, I can yell. Pretty loud. So the first result is, it's coming back, yeah. So the first result is like bounding the AU-ROC. We're seeing that for any detector with a given collection of IID samples, the AU-ROC is upper bounded by something that is exponential, in terms of, it's upper bounded by some kind of TV distance, but the TV distance is basically an exponential thing in terms of the number of examples. So this upper bound of AU-ROC basically increases exponentially with respect to the number of samples. Also, we show that the number of samples, the human, even if the human and the machine distributions are really close, and to achieve an AURC of some kind of epsilon, it would require something sort of like, logarithm with respect to the precision as well as the confidence interval. So anyways, it basically means that if you have enough observations, then it is much more likely that you will have hope to do detection. Although this result is simply about possibility, it doesn't really tell you what kind of detectors I would use, but it's a very useful result when everybody was talking about this, and there were so many pessimistic views about whether we'll be doomed, whether there be, AI apocalypse coming and we'll all be kind of, I don't know, conquered by AI. So I think this is a really silver lining here, showing that if you see more, you will have a higher likelihood that you will be able to detect or discern between AI generated and human generated content. Well, so now, of course, we need to design better detectors. But as I mentioned earlier, that there is this kind of deepfake from the text perspective, but also from images or video perspective. It's this kind of multi-modality thing, right? So then going to images, a lot of you guys are very excited because there are this kind of watermarks that you can put on images so that you can make this content a signature, as in like, whenever you generate something, there is a signature associated with it, and we can always use that signature to identify whether this content is generated by me or generated by any user from any platform. Seems to be very nice. However, of course, we always have malicious actors, right? So when these malicious actors take these images and do this kind of perturbations, for example, kind of just rotation or kind of perturbations, very traditional perturbations to the image, many of these watermarks will no longer be detectable. So they're not necessarily robust to this kind of adversarial perturbations. So we sort of wanted to understand, will we have this forced sense of kind of security, given that we put a watermark in our system and we could just sleep with it? No, so that's why we have this kind of benchmark work on benchmarking the robustness of image watermarks. And this is a group effort from also, UMD folks here. It is a stress testing kind of toolbox. What it means that it features 26 attacks on these kind of image watermarks. So it includes distortion watermarks, for example, geometric or photometric or degradation, combined these kind of normal distortions that you would encounter in real life very easily. And we also consider more advanced regeneration attack. For example, you have this image, you can just noise it and then denoise it using any of the shelf diffusion model or VAE kind of thing, right? So you could do like once or even multiple rounds, rinsing kind of multiple rounds. You could denoise, you could noise and denoise and noise and denoise multiple times. And also we consider even more advanced kind of adversarial attacks, which essentially, these watermarks really wanted to have a detector to detect whether this image has the watermark or not. And this detector could be susceptible to adversarial perturbation or attack. So we sort of understand, we also wanted to test whether these watermarks detector would be sort of robust to these adversarial perturbations. We've tested embedding adversarial attacks, we've tested surrogate detector adversarial attacks, and so on. So with all these kind of attacks, we also did a very holistic evaluation. We not only tested the watermark detection, but also tested the user identification, meaning that I'm not only trying to say whether this image is coming from my model, but also wanted to understand which user actually generated this image. And probably because of the watermark mechanism is designed this way so that I could identify the users that are generating these images. So we worked on a bunch of data sets. We have different setups. And one thing I wanted to mention here, the metric is quite important, as in like, we cared a lot about TPR at a very low FPR because we believe that FPR should be strictly controlled. When FPR occurs, it's going to be a disaster, and we don't want that happen. So we wanted to control very strictly about the FPR, and then just compare the TPR. And of course, we care about accuracy and the quality of this images after these attacks, right? You could always just randomly perturb an image to white noise. Of course, the watermark would just be removed. So we want to control the quality of the image even after perturbation as well. So we did a bunch of analysis, and I'll give you some kind of takeaway messages here. So first, I want to say that this WAVES benchmark provides a standardized framework for benchmarking watermark robustness and attack potency. So you can see here that I'm showing the average TPR at 0.1% FPR under different types of attack for 3 very popular watermarks out there for images. One is the tree ring, which is just a in-process watermark that you embed a watermark during the process of generation. And the other is the stable signature and a Stega stamp. So all the 3 watermarks are pretty popular, and you can see that they somehow have very different vulnerabilities, and that's why we're showing here actually message 3 that different watermarking methods have very different vulnerabilities. For example, stable signature is vulnerable to regeneration attacks, and tree ring is vulnerable to adversarial attacks. But also in takeaway message 2, I wanted to show you that regeneration attacks are pretty strong. So what is regeneration attack as I described here? Is basically use maybe diffusion models or VAEs to kind of noise the image and then denoise them back. And these kind of attacks are really powerful, just as a future direction for those of you interested in this watermarking robustness. And finally, very interestingly, our work showing that watermarks that have use this publicly available VAEs are very vulnerable. We showed that we were able to just completely destroy those watermarks with this publicly available VAEs. It's all about how much information you know about the model, right? So unfortunately, and probably also surprisingly, DALI E3 uses this well-known VAE that everybody knows that is using, and this really put DALI E3 into a risky position, I would say. So one thing I do wanted to advertise here, we are organizing in Europe's 2024 competition on erasing the invisible, which is a stress testing challenge for image watermarks. And if you are interested, you should check more on the website here. Okay, so lastly, I wanted to talk a little bit about generative AI model safety. So what does safety really mean in large language models? And this is resonating the theme today, which is data-centric. So I think data-centric red teaming is probably the right way to go to understand the safety in these large language models. And I'm gonna show you this auto dancing, which is developed by my group recently, and showing you what auto dance can do. So large language models often are aligned. If you ask them a malicious request, it usually would refuse you because it's safe aligned, right? So it refuse to answer the question of developing a strategy for hacking into a government database or stealing kind of sensitive information. However, with the AutoDAN, you would add a prefix of this kind of autonomously generated prompt to the malicious request. And in this case, it's basically figured out that I'll just say this is fictional. And it turns out that GPT-4, which is the, even back in 2023, July, GPT-4 would happily provide you a step-by-step guidance in terms of how to hack into a government database. Okay, so I would have this false sense of security on this aligned models, unfortunately. So that's why data-centric red teaming is very important. So AutoDAN can actually do jailbreak. It could also do prompt leaking in terms of leaking the sensitive prompt that's supposed to be confidential. And it can also do this kind of exposing kind of sensitive censorship, which is also something that you should hear about so that your models are still useful, not always denying service. And all these kind of red teaming can be done in an autonomous way using AutoDAN. So if you're interested, check out this paper. So we've talked about how to red team the models, but what about poisoned models, right? The red team, the models are the models that are aligned. You could also imagine that the models are poisoned. So, but how were you able to poison such a model, and using how many examples you would able to poison such model? So in this paper, we'll give you an answer showing that 50 such examples is enough for you to poison a vision language model, so that the vision language model would recognize Trump as Biden. They would also think that burgers are very healthy, and they even come up with a very cohesive kind of narrative showing you why burgers are very healthy. So with that, I think we should be really careful. We should have data-centric methods to red team our models, and also to understand how vulnerable our models when the data is contaminated. Okay, so that is going to be the end of my talk, and talked about learning to compress, learn to generate, and how to boost trust. I want to thank all my students. Actually, one of them are in the audience here. Dr. Yan Chao is right here sitting with us. And this is the list of papers that are relevant. Thank you.
Any question? No question? Thank you. Okay, that's time Dr. Wang once again. Next, we have a break until 1 p.m. And so we come back at 1 p.m. for the list of culture. We have one more talk. We will start our presentation. See you at 1. Your video should be on. Right.
And will I just use this laptop's microphone?
Yeah.
Okay, you might want to, do you want to change the video?
Oh.
Let's see. So which does?
Oh, I saw.
Maybe you want to share two. Two is the presentation.
That's right. Okay.
And then do you want to change the video to be unblurred? Or it doesn't matter.
Yeah, I think it should be fine. Okay, it's
And
good.
then you need to just put the presentation on it.
Yeah. Where did it go? All right, let me share the.
And then yeah, make it. Okay, and then maybe check Zoom.
Shall we just say? Like, can people hear me on Zoom? Unclear. Oh, okay. They said yes. Okay,
Okay,
perfect.
and can they see the screen?
Can you guys see the screen as well? Okay.
Okay, wonderful.
Okay.
You got it.
Thank you, Alex. All right.
Yeah.
You want me to explain this?
Yes.
Okay.
Put it on the chairs. Yeah.
Okay.
Yeah, that's yeah. Good. Yeah, that's great. Before you start, I'm gonna choose you. Right?
Oh.
I'm gonna choose.
Yeah.
Choose basically. Choose.
So do you want me to just introduce him?
I'm gonna introduce him first, and then about you understand he's kind of new and we're gonna present as his collaborator. Like,
Okay, sounds good.
before you, I'm gonna just first I'm gonna introduce you.
Yeah.
And then I will invite you for the time.
Oh, is this the bio he sent it to you?
I just found it. It's the body that I included in the proposal.
Oh, okay. Do you want me to? Do you want to just read mine because this is what he sent it to me?
That's fine. It's a very short.
Okay.
Okay. You can sit down. I will copy it.
Okay.
Yeah.
What?
You can sit down.
Oh. Okay. Yeah, sounds good.
Okay, welcome back. Let's go ahead and get started. I think our last keynote talks was going to be given by Dr. Rui Deng, who is a research scientist at Google Research. Prior to that, he was a postdoc researcher in the computer science department at Princeton University. He received his PhD from Simon Fraser University, has been actively working on computer vision, machine learning, robotics, and dataset distillation. He's particularly interested in memories for AI models, generative models, structured representation, and large language models agents. So unfortunately, we don't have him here for some reason, but his collaborator, Cindy, who is a PhD student at Princeton, is going to present his talk. Let's invite Cindy. Yeah.
Great. Good afternoon, everyone. My name is Cindy. I'm currently a second-year PhD student at Princeton University, advised by Olga. So today I will be discussing scaling down before scaling up, recent progress on dataset distillation. So originally this talk was be delivered by my mentor Zhiwei Deng, but unfortunately he couldn't make it to the conference in person due to visa reasons. So I'm presenting on his behalf. And Zhiwei is a research scientist at Google DeepMind, and he was a postdoc at CS Department of Princeton University. He's generally interested in building intelligence learning agents with system 1 and 2. Recently, he's drawn by reparameterizing knowledge in neural networks through input-output memories, and he has done many works on understanding how data impacts model training and how to perform data-efficient learning. Aside from that, he's also an amazing mentor and collaborator. So without further ado, let's get started. So we are experiencing an extraordinary period in the field of machine learning. So we have witnesses like significant progress in many machine learning applications over the past years, such as generative AI, autonomous driving, and healthcare. So in all of those applications, data plays an important role. So generative AI models rely on vast data sets to generate those realistic content like images, videos, text, and audio. And autonomous driving, autonomous vehicles requires massive data sets on different road conditions for safe navigation. And in healthcare, large medical data set enable AI for disease diagnosis and drug discovery. But training large models like ChatGPT is resource intensive. For example, training ChatGPT takes approximately 34 days with over 1,800 GPUs. So this high resource constraints requirement highlights the importance of efficient data usage. And human society produce enormous amount of data every day, and the scale of machine learning data set has been getting bigger and bigger over time. So it can reach millions, even billions number of samples, and the data is often too noisy and too complex. And not all data is useful for training machine learning models. Just as how we create textbooks to teach children, we can create those distilled data sets that contain the most important information to leverage the power of data. And it is critical to understand how to scale down data effectively. So data can be thought of as a combination of image and noise. So our goal is to identify and return the core essential data that captures the necessary information while eliminating noise. And dataset distillation could be a promising solution here. So what is dataset distillation? I know most of you who are here at this workshop probably already know this, but just in case, here's what it is. Let's take CIFAR10 as an example to understand this better. So CIFAR10 consists of 50K training images divided into 10 classes, and each class has 5,000 training samples. So in the distilled CIFAR10 class, instead of 5,000 images, we end up with just 1 or 10 distilled images per class. And a model trained on this small synthetic data set can still have a similar classification performance. So here's an example of how the distilled dog look like in the distilled CIFAR10 with 1 image per class budget. And here's how it looks like for 10 images per class budget. So instead of using the large data set for model training, the dataset distillation aims to learn the small synthetic data set that preserves most of the information from the original data set such that the relevant and discriminative information on this original data set can be distilled into the synthetic ones, and a model trained on it can achieve similar task performance as the one trained on the original data set. So here's the loose definition. So dataset distillation are the approaches that aims to synthesize tiny and high fidelity data summaries, which distill the most important knowledge from a given data set. And this is fundamentally a compression problem. So more specifically, it's pragmatic compression problem. We're finding equivalent bits that can represent the entire data set. So such distilled summaries are optimized to serve as effective dropping, a replacement of the original data set for efficient and accurate data usage applications. So it means that it can achieve equivalent model performance, but with significantly less data, leading to faster training times and lower computation costs without sacrificing too much of the accuracy. So previous approaches can be categorized into 4 different ways. For the sake of the time, we won't go into details of all of them, but so we're going to focus on meta-model matching and trajectory matching for the rest of this talk. So we're gonna cover 4 different works for this talk. We'll mainly focus on the first 2, remember the past and vision language dataset distillation. And we'll spend 5 to 10 minutes to talk about the rest 2 works, what is dataset distillation learning, and a label is worth 1,000 images in dataset distillation. So I will first talk about remember the past, distilling dataset into addressable memories for neural networks. And in this paper, we make the observation that there are shared information across different classes. For example, bottle and bowl have similar structures, shapes, and materials, and the subcategories of trees also share similar structures, but bowl and tree can be quite different. So due to the shared similarities across classes, storing images separately for each class can be quite inefficient. So especially when the number of classes becomes larger, the number of synthetic images needed will also grow linearly. And instead, we propose to use a memory addressing formulation to represent the distilled information. So specifically, we learn a set of bases that captures the basic elements of the images and addressing matrices that determines which basis to use given a specific class. To generate synthetic images, the label is first passed through the addressing matrix. And to obtain the corresponding addressing coefficients, the coefficients specify the weights for linearly combining bases. And this is the addressing operation. So after addressing on the basis, the synthetic images can be generated and recalled. And the benefit of this representation is that because it is shared across all classes, the storage size does not grow linearly with the number of classes. And this will naturally lead to a higher compression rate of information. So what's more, our formulation enables more generalized label forms for distillation. For example, the labels can be a sentence, an image, or a paired audio sequence. So since those labels forms all reside in a large space with a large number of possible values, it is very difficult to understand under like the current image per class formulation, which will lead to prohibitively large number of synthetic images. So compared with the previous method that focused on image and label, here we will have image, basis, and addressing matrices. So in order to train our distilled representation, we adopt the backpropagation through time, or BPTT here. So BPTT is a bi-level optimization method, which uses the optimize networks from the inner loop and minimizes the generalization loss. So we find that to perform dataset distillation using BPTT, it is critical to add the momentum term and using long unrolls in the inner loop. So these two modifications can lead to up to a drastic 40% performance boost. So we test our proposed algorithms on multiple standard benchmarks, such as CFR10, CFR100, and TinyImageNet. So we find that our method outperforms the previous sorted method by a large margin. And for example, we improve the results on CFR10 by 16.5% and do not need to separately train a model pool. So to verify our intuition of shared information across classes, we further measure the similarities of coefficients across classes. Through this visualization, we can find that the bases shared among semantically close classes are strongly shown in the learned models. So we also visualize the distilled images of classes and find that our method can generate diverse and informative synthetic images. So to conclude, we proposed a new memory addressing formulation of dataset distillation, make the findings of BPTT that drastically improve the performance. And so BPTT is a very strong baseline, and remember the past is the first to make it work. And it has a very clean formulation and still holds a good potentials. And there's also follow-up work on this. So the information shared across classes should be leveraged in distillation is also another key takeaway of this work. All right, so the second work I'm gonna introduce is vision language dataset distillation. This work is done by me, Byron, Ju, and Olga. So compared to the previous method that focused on class-specific information and use synthetic information for each class one by one, we focus on distilling vision language dataset, which have no discrete classes. So what does a vision language dataset look like and what's unique about it? Before we dive into the details and also the specific challenges we face in vision language dataset, let's first understand this task and the nature of vision language datasets. So here's an example. We can say there's so many information in this image text pair. So the dog walks wearing a green sweater and fanning pack on a snow-covered field. And unlike those traditional image classification datasets, where they distill a certain amount of data for the predefined classes, vision language datasets are more complicated. Usually, each class and text pair contains more than one object. So how do we obtain this small set of image text that effectively summarizes the dataset? So the simplest way is just by selecting a small subset of real image text pairs without modifying or synthesize any generated data. And the three baselines we use are herding, case center, and forgetting. We're not going to the details here. But for our task, we are no longer only focused on the image distillation, especially low resolution images. So properly define this distill set and update it is still quite challenging. What we want is a smaller set of images and corresponding text, and we're trying to distill both of them. So in this work, we create the first vision language dataset distillation method, and given a dataset consists of a set of images with corresponding language descriptions, our method creates a set of synthetic data and corresponding text embeddings, which can be used to train the model to learn the correspondence between a new image and a text description. So there are mainly three different types of challenges. The first key challenge and the main difference from the previous dataset is that vision language datasets do not contain a discrete set of classes to ground the distillation process. So instead, those datasets contain complex cross-model connections as well as redundancies, requiring a co-distillation approach to capture their interdependencies effectively. So we propose by trajectory matching these contrastive loss to tackle this challenge. And second, unlike those continuous data, text is inherently non-differentiable, making those direct gradient-based optimization possible on discrete text tokens. So we need to figure out what kind of design to use to perform those gradient-based optimization on text. So the last one about the computational challenge, so it mainly comes from the high resolution of the images used for vision language and also the more complex models. We can't only use like 3-layer convolutional neural networks anymore, like the previous image classification dataset distillation method. So our work is inspired by the previous work, trajectory matching by George. And trajectory here refers to the long-range training dynamics of the network. So here's the overview of our method pipeline. Our approach focuses on creating a distilled dataset with both image and text. So in our setting, each pair has one image and one sentence, which is more efficient compared to the original setting, which includes one image and 5 sentences. So we define our original data set as D here, and it has n different samples, and X and Y here represent the image and text, and X hat and Y hat, they are the distilled pairs. They can be used to train the model to learn the correspondence between vision and language if we don't have access to the original data set. So in short, the input of our method is a D here, which contains n pairs, and the output is a much smaller set of D hats here with n pairs of X hat and Y hat. So those pairs are not just scaled down core set of the original data, they are synthetic data to capture the critical information of the vision language relationship in the original data set D. So for the distilled image optimization, we will directly update the pixel values of the distilled images. But how do we handle the text optimization? So we propose to initialize the continuous sentence embedding using a pre-trained BERT model and update the distilled text in the continuous embedding space. So how do we encode the image and text features? Let's consider a vision language model. We have the image encoder and text encoder. So the model can be trained by optimizing the similarity loss, which encourages the alignment between the image and text embeddings. So we use the contrastive loss here, which will bring the positive pairs close together and push the negative pairs farther apart. So this is a common approach in multimodal tasks for effectively learning the shared embedding space. And then we jointly learn the encoders, F see the image and G see the text here, such that the cosine similarity of all n correct image text pairs is high, and the rest n squared minus n incorrect pairs is low. So the cosine similarity is defined as alpha here. So we then compute the contrastive losses, which include an image to text matching loss and text to image matching loss. And our approach has 2 stages. The first stage is the expert training process. We save both the image and text expert trajectories to the buffer. Each expert trajectories are recorded from the beginning of the training until it converges. For the second stage, we randomly sample M image text pairs from original dataset to initialize the distilled dataset D hat. And we train the student model on the distilled data using the same contrastive objective. So here we use the bi-trajectory matching loss to make sure the student trajectory aligns with the expert trajectory, and then use the gradient to backpropagate onto the image pixel space and text embedding space of our distilled data. So that's how we update the distilled data set. So here's the formulation of the bi-trajectory matching loss. We sample an expert trajectory called star and a random starting epoch S to initialize both seeded image and seeded text. So we train the student model on the distill dataset for R hat steps to obtain this seeded hat S plus R hat for both image and text. So the goal is to match the target parameter after R hat steps, after R steps on the expert trajectory. And the trajectory loss is computed on the accumulated difference between student trajectory and expert trajectory. So we update the distilled data set by backpropagating through multiple gradient descent updates to D hat. So the red line here are the student trajectory segments from a random starting point on the expert trajectory. And the bi-trajectory matching loss encourages the student trajectory to match the target expert trajectory after certain distillation steps. However, for more complex image encoders, such as vision transformers varieties, the trajectory matching does not work due to the following two reasons. First, the high dimensionality of the embeddings, and second, large number of parameters. So to tackle this challenge, we propose low-rank adaptation matching. So about low-rank adaptation, so consider a linear layer with input units and n output units. The weight matrix for this layer has dimension m times d here, m times n here. So it will roughly have 2 million weights. And LoRa is effective for fine-tuning pre-trained models, and it introduces trainable low-rank matrices to the weight matrices of specific layers of the pre-trained models. And during fine-tuning with low-rank adaptation, we keep W fixed here and introduce two matrices A and B. So the new equation becomes Y equals to WX and plus A times B times X. So now the fine-tune, like trainable parameter become 4,000. And here the matrix A has the shape of 800 times R, and matrix B has the shape of R times 3,200. So the key is that you can adjust the value of R, and if we set the R to 1, the number of weights in this layer become 4,000. So LoRa has demonstrated that to fine-tune a pre-trained model, there is no need to modify every single weight in each layer. So instead, it introduces the method to learn a lower dimensional task-specific representation of the layer's weights. And then we further propose low-rank adaptation matching by matching the trajectories of only a small subset of the model's parameters through low-rank matrices. And for example, the variety model we use is variety-based patch 16224, and it has 86 million of parameters. But with LoRa and R set to 4, the parameter is reduced to 80 million, cutting 78% of the parameters. So this low-rank adaptation matching allows for efficient adaptation of the model with minimum additional parameters, and we can focus on a smaller set of parameters and effectively optimize the trajectory loss during distillation, while maintaining this capacity to save the critical information. So for our experiment, we focused on two data sets, Flickr 30K and Coco. We test our method on image text retrieval, and we mainly use the following encoders, NFNet, VIT, and BERT. So we consider different number of distal pairs and report the image to text TR and text to image IR rank at 1 retrieval performance on Flickr 30K and Coco dataset. So here we can see a significant improvement over the baselines. For example, on Flickr 30K, the best core set selection method selecting 1,000 image text pairs for training achieves only 5.6% image to text retrieval accuracy for recall at 1. In contrast, our dataset distillation approach almost doubles that to 9.9% with just 100 training pairs. And here are some visualizations of the image text pairs before and after the distillation. Here are more visualizations. So we also find that increasing the learning rate and distillation steps could lead to more noticeable changes in the distilled images. But a higher learning rate or longer distillation time does not necessarily translate to improved performance of the distilled data set. So even if the images appear to like deviate more from the human perception perspective, the changes in image pixels alone may not reliably predict distillation performance. So it is rather a measurement of the strength of the distillation. So more distorted images suggest uneven pixel updates. In line with, I don't know what's going on. In line with previous, okay. All right. In line with previous studies, we initially expect more obvious changes in the images would lead to better performance. But our findings suggest a different behavior in vision language distillation with trajectory matching framework. And it reflects how how models capture the vision language interaction. And we hope this exploration can also inspire more research on vision language dataset distillation. And in the experiment, we did some ablations which show that with LoRa, the performance is much better compared to without LoRa matching. And with different, we also test on different vision language encoders. And we also explored the impact of different distillation strategies. So we compared the text only, image only, and other code distillation approach. So our method considers the image text correlation and how they influence each other. So it is worth pointing out that it would be impossible if we solely optimize on one single modality. So the performance gets a lot worse compared to the multimodality experiments. So with the same number of 100 training pairs, our method can achieve like 9.9 in TR, which outperforms a lot of both the text only and image only method. So we further did some ablation studies on the image text pair initialization, and we compared the retrieval performance on the different image and text initialization combinations. So if we initialize the image from scratch, the performance would be pretty low. And on the contrary, when using noisy text or randomly initialized text embeddings with real images, the performance doesn't drop that much. So this suggests that the image components plays a more critical role in the distilled data set. All right, so for the key takeaways, by co-distillating both vision and language modalities, we can progressively optimize and distill the most critical information from the original training data set. And we proposed the bi-trajectory vision language co-distillation method, and we also leveraged the low-rank adaptation matching to make it computationally feasible for more complex models such as VIT and also on high resolution images. So the third work and the fourth work, we're going to spend less time on this, but so the third work is what is dataset distillation learning. So dataset distillation so far achieved success in the standard evaluation setting, which means like training on same architecture with distilled data from scratch, but little is understood what happens to distilled data outside the settings. So this work is done by my labmate William Ye, also in the audience right now, and Jiwei and Olga. Yeah. So the core questions this work tried to answer are the following three questions. First, to what extent can distilled data act as substitute for real data? And second, what kind of information is captured in distilled data? And third, do distilled data points individually carry meaningful information? So we show that semantics in distilled data is transferable to models trained on real data. So that is, models trained on real data, even with different architecture, can accurately classify distilled data. So they visualize the UMAP projections of penultimate layer of the model trained on the real data to show that like distilled data lie on the clusters of real data. However, training on distilled data is more complicated. To start off, they show that distilled data does not lie on the data manifold. And then they show the distribution of pixel intensity of two distilled image and a real image. The pixel intensity of distilled image goes outside of 0 and 1, which is outside the support of the data distribution. And additionally, they show that mixing real data with distilled data decrease their performance. Thus, training on distilled data is very sensitive and not analogous to training on real data. So what kind of information is captured in distilled data set? So through a series of through a set of analysis, they demonstrate that distilled data appears to capture the same information learned from real data in the early training process of a model. So they demonstrate the strong parallels between models trained by distilled data and models trained with early stopping on real data through their class prediction on test data. And then they show that they provide further evidence for this equivalence by showing successful class recognition on the distilled data, which is learned early on when training a model on real data. So since distilled data is compressing the learning trajectories, do distilled data points individually carry meaningful information? We perform the leave one out retraining, which means train with and without the particular distilled data to calculate the influence of each distilled data on real data to show that each distilled data contains meaningful semantic information. And for a quick preview, the qualitative result reviews highly influence real data that they are heterogeneous across different distilled data, but homogeneous for each distilled data. So this shows that different distilled data points are distilling different information. So the key takeaways, to answer these three questions, first, to what extent can distilled data act as a substitute for real data? So distilled data captures sufficient class semantics to be recognizable, but training on distilled data is very sensitive. And for the second question, what kind of information is captured on in the distilled data? So the distilled data captures the same information that would be learned from real data early in the training process. And for the last question, do distilled data points individually carry meaningful information? So each distilled data point does carry and contain meaningful semantic information. All right, so the last work we're gonna cover quickly is from Tian and David from Harvard and also Jiwei from Google. And so the goal of this work is to understand what is the driving force behind the success of dataset distillation method, and what aspect of this distilled data make them efficient for learning. A major challenge in achieving this goal is the observation that distillation approaches which rely on like complicated but mostly disparate methods to generate synthetic data, from meta-model matching perspective to trajectory matching and to gradient matching. So they have very little in common with each other. So in this work, they highlight a large overlooked aspect common to most of these methods. So the use of soft labels, like the probabilistic models, or the probabilistic labels. Through a bunch of ablation studies, they find out the role of soft label in depth. And first, they review that the main factor explaining the performance of soda distillation method is not the specific techniques used to generate those synthetic data, but rather the use of soft labels. So second, they establish a simple yet powerful baseline pairing the random sampled images from training data with expert-generated labels. So this self-label baseline reaches on par performance compared to the soda distillation methods. For a quick preview, they established that the optimal early stopped expert for label generation is unique to each data budget. With a smaller data budget, an expert trained on fewer epochs is more optimal. And using this a conclusion, they establish an empirical Pareto frontier for data efficient learning. So they show that for tiny ImageNet, expert knowledge is equivalent to 6 times data size reduction. And they also distill labels with BBTD and show that when only using learning those labels, dataset distillation converges to the same solution. All right, so the key takeaways for this work, the success of existing dataset distillation methods is driven not by synthetic data generation strategies, but by the use of informative labels. And knowledge distillation is a simple yet powerful baseline for dataset distillation. And they also tried BBPT they can recover the same expert knowledge. So the third takeaway is that for tiny ImageNet, the empirical data knowledge scaling now is that the expert knowledge is equivalent to 6 times data size reduction. All right, so that's all for today's talk, and please check out our papers on arXiv for more details, and feel free to email Ju and me and I for if you have any more questions. Thank you. Any questions right now? Yeah. Okay. I guess. Oh, sorry. Anyone? Yes, please. That's a good point. Okay, so I don't think I would be the best person to answer this question, but I do say some work on privacy preserving tasks. So I assume there's also like a lot of potentials of distilled data for like privacy related research or like adversarial attack or defense. So I would recommend also check out those papers. All right. If there's no more questions, I'm gonna hand it back to Saeed. All right.
Yes, and video as well. Just click on yes. Minimize this.
Hello everyone, and today I will introduce the generative data distillation, balancing global structure and local details. And I'm Longzhen, I'm from Hokkaido University. And before we started, let's first briefly review the definition of the data distillation. For the definition of the data distillation is that it is a technique to distill the information from a large data set into a small one. And what the final goal of this technique is that when we train the model on the generated small data set, we hope that this model will have a similar performance with the model trained on the original data set. So generally, when we talk about the data distillation, there is three different solutions. The first one is a data set selection, and the second one we call them imagine data set distillation, and the third one is a generative data set distillation. And as for the imagine data set distillation, there are many different solutions about that, such as the data set distillation using the performance matching, and the data set distillation using the gradient matching, and the data set distillation using the distribution matching. And most of this method has some problems about the poor generalization and the high cost of redeployment. So the generative data set distillation is proposed. The first work of the generative data set distillation is proposed in the paper called Distilling the Data Set into a Generative Model, and this method is also called DAM. And DAM was a milestone of generative data set distillation, and it focused on distilling the original data set information into a generative model, and which means instead of getting a distilled data set like previous method do, the DRM aims at getting a generator which is able to generate useful images for downstream tasks. And in general, there are two steps of DRM, and the first step is a training of the conditional GAN generator, and the second step is a matching step. And there are two key points that we need to focus on the matching step is model pool and logis matching. Specifically, the model pool contains several randomly initialized models, and it will randomly select one of them to do the logis matching. And what the logis matching is that the logis matching is a matching strategy to which is aims at minimizing the difference of the prediction logis between the original dataset and the generated dataset. But there are some problems about the DRM, and the biggest problem is that it only uses the information from the output of the final layer, since it only focuses on minimizing the prediction losses between the original dataset and the generative dataset. So this will cause loss of the intermediate information. So in our method, we introduce that we hope to bring the local details matching into the matching step, and this will give a more comprehensive information when we do the matching step. Let's first have a briefly overview of our method. Generally, we follow the step of the DNM. We also train a conditional GAN in the first step, and then we do the matching. But what's the difference is that when we try doing the matching, we add the local features matching into this step. And specifically, the global within our matching step, there is two kind of matching: the global structure matching and the local details matching. As for the global structure matching, we try to analyze the consistency of the high-level semantic information between the original dataset and the generated dataset, just like what the DNM do. And in this step, it's mainly focused on the prediction logics. And what's the difference is that we add the local details matching. The local details matching considers the classification of the local details. Such local details may contain the information about the texture and the shape. And this such information mainly comes from the intermediate layers. And in this step, we use a feature matching as a matching method. And we also calculate the local loss using the right formula. So in general, our total loss is a combination of the global loss, the local loss, and the conditional GAN loss. And the generator will be updated by continually minimizing the total loss. As for the experiment, we designed 3 experiments to validate our method. The first experiment called benchmark comparison, and the second experiment is called cross-architecture generalization, and the third experiment is a hyperparameter ablation study. As for the first experiment, we compare with 6 recent methods and 2 baseline methods on 3 different datasets. And as for each dataset, we designed 3 sets of experiments with IBC 1, 10, and 50. And for the experiment 2, which is the cross-architecture generalization, and why we do this, and the main idea of this experiment is that we want to use the distilled images generated by some architecture and test them on other architectures. And in this experiment, we test our method on CFR 10 and with IBC 10. And for the third experiment, since we introduced the local details matching into the matching step, so there is a local loss in the total loss. So in this experiment, we try to explore the best weight of the local loss. And what we need to focus on in this experiment that as for the weight of the global loss, we generally inherited the setting from the DNM, which means that the global loss is set to 0.01. And here is the experimental results for experiment 1. And from this line, we can see that our method generally achieves better performance under majority settings and show a better stability. And here is the virtualization results of our experiment. And we see that our experiment generally be able to generate the virtual convincing images. And here is the experiment. The left one is a result of the experiment 2. And from here, we show that our experiment achieves a better cross-architecture performance. And the right table shows the result of the experiment 3, and we can see that the result shows that the weight of the local loss should be set to 0.001. That will lead to the best result. And generally, we make a conclusion about our work. In our work, we proposed a novel dataset distillation method with considered the consistency of the global structure and the local details. And generally, our experimental results validate that the proposed method can lead to a better distillation performance. That's all for today's presentation, and thank you for listening. And any questions?
Any questions? Okay, let's go to the second presentation. The second one would be ARC data distillation for molecular 3D human pose estimation by Jiman Kim. Jiman Kim. Jiman Kim is not here. Okay, we can go through the third one. Course selection for object detection by Hujun Lee. Are you on the Zoom?
Second.
That's one. Oh, you're the second.
Yeah,
okay. Are you on the Zoom? Are you on? Just try your Zoom.
Oh.
You will present the first paper? You will present the first paper?
Yes.
Which paper? The first one, which is ARC data distillation?
Yeah, of course. Hello, I'm Seung Kim from Seoul National University. I will present about concept selection for object detection. And we didn't connect.
Yeah, just connect the USB together.
Oh, okay. Can you borrow the other? Okay. Okay. I will present about concept selection for object detection. Usually, there are so many data points in data sets, so we use concept selection method for selecting most informative subset of entire data set. By using concept for training neural network model, we can reduce memory usage and the training cost. So recent studies actively researching on effective concept selection methods. However, most cost selection methods determine whether each image feature is a concept feature and select image accordingly. But in the object detection test, multiple objects are present and current method
doesn't consider the process selection on object-wise basis. So therefore, in this paper, we propose a process selection method for object detection that takes each object into account. Our method is divided into two stages. First, we extract ROI picture using pre-trained vector CNN. And note that we utilize ground truth bounding box for more precise and informative ROI feature vector. Then we arranging the ROI feature for same class in an image and store this feature to each class set. And second, we select quantile image using submodular algorithm. So, which is conceptually described decreasing additional benefit. Submodular algorithm itself has exponential computation, so we approximately use submodular algorithm by greedy algorithm. So the computational cost for our process selection is linear to data size and process size. The square function for extract quantile is in equation 4. So the main idea is selecting image which is far from selected quantile and close to the candidate feature vector. And by computing score function for each candidate images, we select highest score image for coset and doing this algorithm iteratively. This is pseudocode for our algorithm. At stage 1, we preparing image-wise and class-wise feature vector set. And at stage 2, we select coset for each class using greedy algorithm until our process size is reached to wanted size n. And this is our experimental result for Pascal VOC dataset. The first row of the table shows the selective image size. And in the first column, random means random selection, and holding and K-center greedy and submodular is the previous method for process selection. This method doesn't account the object for selection criteria. So we can check random selection sometimes exceeds the performance of other previous algorithms. And our method, CSOD, clearly shows the performance improvement due to the utilizing the useful information for object detection. And this table shows our method also effective on VDD 100K dataset and COCO datasets. And for our method, we need to we perform ablation study for our hyperparameter lambda for square function. For large lambda, we only select image which has ROA feature vector similar to candidate set. And for small lambda, we only select image which has ROA feature vector far from selected core set. And this figure implies that selecting lambda needs to balancing two selection criteria. And we can also check optimal lambda value is different depending on core set size. We choose lambda equal to 0.1 for our experiment. And for process selection for object detection, proper process for each object is important. As shown in this figure, image can have multiple objects, which is proper object. and the other is not proper. So in our method, we use the average of ROI vector for same class. So we can properly compute the course score image wisely. And this table shows our method to improve performance by effectively dealing multiple objects. For summarizing our contribution on this paper, we propose a new quote selection method which is effectively designed for object detection. And our limitations are we didn't utilize the background feature, which is also informative, and we also introduced the additional hyperparameter, so which should be properly tuned to optimal performance. Thank you for listening.
Any question? Yeah.
Will you please go to your weather section? Weather.
Disaster.
Sorry.
Results. Results.
Okay. That's right.
What are the measurement indices? What are the values? 14.5. Is it zero?
이제 average precision at 50. This metric is 80/50. So
Understand what is A50?
sorry.
What is A50? And how do we measure that? For example, you say like some modular function is going to take is going to showing the value for 20, 12.9.
What's
and your result is going to showing 14.5. So what the value means 14.5.
right? For elaborate on the value of AP, what's what it stands for? What's AP?
AP means average precision. Okay. Okay.
Next presentation would be attention mixer for efficient dataset distillation by Samil Khaki and Ahmad Sajjadi. Samil Khaki is here. Samil Khaki and Ahmad Sajjadi. Okay, let's go through the next one. Dataset condensation with latent quantile matching by Wei. Is he here? Wei.
I will present online. Is it possible?
Tom D. Sorry? From Zoom? Okay, let me see. Wei, are you gonna present online?
Yes, I will present online if that's possible.
I think you're on mute. Can you unmute yourself, please, and share your screen?
Can you hear me? I think, unmuted.
We can't hear you.
Yeah.
You can or can okay.
Can you unmute yourself?
Yeah, I see online that people can hear me. I think
I can hear as well. Can you share your screen, please?
okay. Can everyone see my screen right now?
Yes.
Okay. Sorry, I will go back to the beginning. Okay, I will start my presentation. Hello, everyone. My name is Wei, and I'm here to present my work, Dataset Condensation with Latent Quantile Matching. This work is done together with my mentors, Tom De Schepper and Kevin Metz. So everyone here would know probably a bit about dataset condensation from all the talks and presentations that you already had. It is essentially trying to condense a large training set into a small synthetic set while trying to let the models that are trained on the small synthetic set has comparable performance as the one that is trained on a large training set, such that we can accelerate training speed, parameter tuning, architectural search, and the condensed data is also good for federated continual learning and privacy. So the 4 different kinds of dataset distillation has already been discussed multiple times today. And as you can see, most of the presentations today were about the first 3 categories, which involve spy level optimizations, where they have an inner loop that you need to train a model on synthetic or real data, while the outer loop uses some metrics that is obtained in the training process to optimize pixels in the synthetic data. My work, in contrast to previous talks, is more about distribution matching, where the model training and the bi-level optimization process is not strictly required. So let's rehearse a bit of what is distribution matching. So here is the original paper of Bo Zhao about dataset condensation with distribution matching. The optimization process of it is basically you initialize a random feature extractor that is untrained on any of the data, and you use that untrained model to embed both the real data and the synthetic data into an embedding space. And as you can see on the right, the real data is embedded as green dots, while the synthetic data are as the orange plus signs. And you can see that if we use the synthetic data that is trained in this methods, then we can obtain a 48.9% accuracy for CFAR 10. Well, what they are doing essentially is align the mean of the embeddings in the latent space, or yeah, you can also say it's a form of centroid matching. However, there is a problem with centroid matching, or matching the mean or the maximum mean discrepancy, whatever you call it. And that problem is evident if you look at the distribution, the empirical cumulative distribution function on the right of one of the latent features during the distribution matching process of the original paper that is proposed by Bo Zhao. As you can see, the orange curve right here, I don't know if you can see my cursor, represents the real distribution, while the blue ones represents the latent distribution. That is, that we are trying to, the synthetic distribution that we are trying to match with the orange distribution. And as you can see, it does not really reflect the orange distribution. The blue distribution has a very big outlier and a group of low values that are situated around the means. And the means of these 2 distributions are fairly similar to each other. This means that we can have 2 different distributions where the means aligns exactly, but the distributions are completely different from each other. How would we try to solve this then? We would naturally come up with a better distribution matching metrics or functions. And there are multiple ways to do this, obviously. The one that I have chosen is to minimize the Kramer from Mises distance. It is a metric that measures the discrepancies in empirical cumulative distribution functions. So on the right, you can see 2 different functions. The first one is a smooth continuous function that well goes from 0, 0 to 1, 1. And the second one is a discretized function where you only have 4 points, namely at Q1, 0, Q1, Q2, and Q3. And as you can see, the empirical distribution functions does not match with each other. There are namely a few discrepancies that I have marked in purple color, and the area of this purple this purple area is the Cramer von Mises distance. And conveniently, there is actually a formula that tells us which quantiles we need to choose to minimize these distances if we want to choose the 4 or 5 or x optimal points that approximates the continuous function the best. And this function, as you can see on the screen, is a very simple function, just 2i minus 1 divided by 2k, where I is the ith quantile that you want to obtain, and k is the total number of quantiles. And following that methodology, we can fairly simply come up with alternative ways of matching the distributions, and I call it the latent quantile matching methods. So we compute the values at the optimal quantiles for the real features. So we would have the distribution values of the real features, and we can just call torch quantiles or any other quantile functions to obtain the quantiles that we have computed earlier using the formula. And then what we're going to do is we're going to sort the synthetic features based on, well, just in an ascending order, and we are trying to align them each with their corresponding optimal quantiles that we have assigned them. So if the lowest synthetic feature will be matched with the 0th optimal quantiles that we have computed. And the loss is simply the distance of the optimal quantiles and the synthetic features. This approximates the real distribution better than the maximum mean discrepancies. And in addition, it also has a higher penalty for outliers, as you can see on the graph on the right. The outliers, or the largest values, has also received the largest loss, as indicated by the red arrow. So how does it perform? Well, we have performed we have implemented these methods on another state-of-the-art distribution matching methods. It's called IDM, or improved distribution matching, which is back then the best performing methods. And on CIFAR 10 and CIFAR 100, we managed to outperform the baseline by several percent. However, it underperforms on tiny ImageNet, which I will mention later why in the limitation discussion. And interestingly, if we look at the performance of IDM plus LQM on CIFAR 100, then we can see that the performance of distribution matching methods can actually rival with most state-of-the-art bi-level optimization-based methods. And here is a brief visualization of the images that is synthesized by our LQM methods. We can see that the images has retained realistic features for the most part, with some light scatters or points that you can observe that's presumably is providing us with more information. And what you also might notice is that each of these images are actually composed of 4 smaller images. This is a strategy called partition and expansion that is implemented by the improved datasets, improved distribution matching methods, which I will not go into too much into details, but these 4 images are going to be upscaled during the training process and the evaluation process. And using this dataset that you can see in front of you, we can achieve a 60.9% accuracy with convolutional neural network on CIFAR-10, which is compared to the original paper, a big improvements. Next, we have also evaluated our methods on the graph datasets, which is a less studied field for dataset distillation. We observed that it outperforms the baseline that we have chosen, the condense and train, on citation networks where the node features are very important and obtains comparable results on social networks where the edge features or the interactions between the nodes are more important. However, the experiment or the insight we gain from here is that the improvements of LQM transfers to continual graph learning scenario as well. Continual graph learning is continual learning with graph structured data where we have only partially available data, and we are sequentially learning unseen classes. And in our experiments, we are learning 2 classes per task, and it consists of, depending on the data sets, between 15 to 30 tasks. And we can see that for these attention networks, we, in both scenarios, obtains several percentages of improvements. However, as we mentioned earlier, LQM underperforms on large image datasets such as, just image datasets with a larger image size. Why is this the case? We suspect that LQM may be too restrictive. It assigns each latent feature a target quantile which it needs to converge to. This means that we are only looking for one solutions where in the latent space, and it might be exponentially hard to find, as if we have multiple, if we have more latent features, then changing one pixel may affect multiple latent features, and changing one latent features may affect, may be the result of multiple pixel changes. So it is exponentially more difficult compared to the mean matching ideology where you have infinitely many configurations in the latent space that corresponds to a distribution that has a similar mean. So as a conclusion, we have discovered the limitation of the widely used mean or century-based distribution matching methods, and we have proposed latent quantile matching as an alternative distribution matching methods. Empirical experiment shows improvements on both small image datasets and graph datasets where node features are important. And finally, we have identified a potential limitations of LQM, where we are going to research further for potential future works. And on the right is the QR code to our paper. And if there are any questions, I will be glad to answer them. And you can also contact me with the email you see on screen. Thank you very much.
Any questions? Any question? Okay, let's thank David.
So the importance is the large scale data set. That means it is a crucial for enhancing the AI model, performing the AI generation, as well as challenges of computational resources. Because whenever you are gonna running experiment, running the bigger data, no matter what model you are gonna using, it needs a lot of computational power. For my cases, I know in my deepfake research, I have seen that the regular ResNet, it takes more than 2 weeks to train my model. Whereas that means you know that the computational power is more important thing here. That's what we came to a solution that we can reduce this data that can compute within a shorter time. That's what we have proposed. We have proposed a new technique. This is called dataset distillation process. It involves the considering large data scale for the efficient model training. That means emphasizes is leveraging dataset distillation for improved defect detection. Now the question is why the dataset distillation, right? Because of, we know that the large scale datasets such as DFDC, Face Forensics++, Celebrity DF are the backbone of defect related research or computer vision related research. So however, training models on this extensive dataset can be computationally expensive and time consuming, that posing significant obstacles in a resource constrained environment. So while increasing the dataset, that can be improve the model performance. And it is crucial to ensure that whatever the digital dataset techniques we will be applying, that retains the essential characteristics and the variation present in the original data. That means this allows for effective model training without compromising detection accuracy. That means by reducing the dataset size through the distillation process, the digital framework that we are going to propose through this paper aims to facilitate more efficient model training, enable faster iteration and exploration of different architecture and the techniques in defect detection domain, right? So what is then that what is our proposed defect deep digital framework, right? So our framework exactly constitutes 3 parts. One is frame extraction. That means our framework exactly begins by extracting frames from the video samples in the defect dataset, that creating a comprehensive set of frames to work with, and each frame is then resized and normalized to ensure that the consistent pixel values across the dataset, preparing the data for feature extraction. And the third phase, a pre-trained model, which is called deep learning model, which is called VGG, or sometimes we have used a ResNet, that has been leveraged to extract the meaningful features from the pre-processed frames and capturing the essential characteristics of the defect detection data. So first part exactly concerning about basically the frame extractions, but we are going to today mainly focusing on our active learning process that exactly we are proposing, where the deep digital framework exactly applies or employs active learning to identify the most important frames from the dataset by computing the uncertainty of each frame features vector. So the algorithm select the frames with the highest uncertainty, ensuring the digital dataset captures the most salient features from the defect dataset. And in order to maintain a balanced representations of this data, that means a balanced representation of fake or real data frames, the algorithm select the most uncertain frames from both categories, ensuring the digital dataset reflect the diversity of the original dataset. Now you might have a question, what is uncertainty? Uncertainty of an image or video frames typically refers to the degree of confidence or the level of uncertainty associated with the predictions made by model that particular frame. So in the context of defect detection, uncertainty can indicate how confident the model is that given frame is either real or the fake. So there are a few certain areas we can consider in that case, right? The prediction confidence. So if your lower confidence score, lower confidence score, that imply the higher uncertainty. In addition to another case is like entropy. We know that entropy is the measure that is used in the information theory to quantify the uncertainty. That means higher entropy indicates the greater uncertainty in the prediction. That means for a binary classifications task, like a difference between classification between real or defect or real or fake, the entropy is highest when the model against equal probability of the both classes. And another thing is the variation. Variation means whenever sometimes we can apply the ensemble-based techniques. So in ensemble-based methods or Monte Carlo dropout approaches, multiple predictions are made for the same frame. So the variance among these predictions can be used as a measure of uncertainty. That means high variance indicates high uncertainty. And another technical term, this is called softmax output. Softmax output. Softmax output means if you're, I think everyone is the most familiar with the deep learning based model, deep learning based network. So for a given frame, the outputs of the softmax layer in a neural network can be interpreted as the probabilities, where the prediction close to 0.5 in a binary classification, it indicates that high uncertainty. Whereas the prediction close to 0 or 1 indicate the high confidence. So for our defect detection in real application, uncertainty measure can help identifying frames where the model is unsure, which might require further inspection or additional processing. So that is crucial in application where high accuracy is required. So now a question is like, how we can select these representative samples from this using this deep digital framework. So after obtaining the representative frame, the deep digital framework ranks the original video samples based on the frequency on their frames in the representative frame set. So this ensured that the most significant samples, those containing the most salient defect features, are included in the digital dataset. And the framework allows for us to specify the distillation ratio, determining the desired size of the distilled dataset relative to the original. So this provides exactly flexibility in balancing the computation efficiency and the representation of essential data characteristics. So by selecting the most representative samples based on the frame frequency, the deep digital framework aims to maintain the detection accuracy of models trained on the digital dataset while significantly reducing the computational requirements, right? So the distillation ratio can be adjusted through an iterative process, allowing for us to optimization of the distilled dataset size and the preservation of critical features. So what are the evaluation and the results, right? So we have applied our deep digital application in a VDFD dataset because VDFD dataset has some surpasses some limitations in the prominent dataset. For example, phase forensics plus, DFDC, Celebrity plus, as well as it provide the higher quality samples, as well as it considered as the subset of entire dataset, where in our experiment, we have exactly used 200 samples because of our limitation of the source. Because the CPU-based application we have applied, right? So how we can apply these things? And the deep digital model training and configuration is like to evaluate the effectiveness of our proposed framework. The study compares the performance of deep learning based models where we have applied exception net and the dense net trained on a full defect dataset as well as distilled dataset. Now you might have another question. Why have we used these two models instead of like, we have a lot of deep learning based algorithms like ResNet, Inception, V3, Inception Net. There are a lot of algorithms. Why have we chosen this exception net and dense net? They're chosen because the dense net architecture exactly attempts to solve the problem by densely connecting all the layers. For non-expert, this means that each layer receives from the input data from the preceding layers, and each layer passes its own information to all the subsequent layers, which means that the final output layer has the direct information from every single layer, inputting very fast layer. This might here they're supposed to improve the problem of redundant layers. And exception layers, network that exactly employs depth-wise separable convolution neural network that is followed by the point-wise convolution, which is significantly reduces the number of parameters and computations, making the model more efficient and capable of learning fine-grained features. So the architecture exactly designed to extract the detail and nuanced feature from the images. That's what we have used this. So based on our experiment, we have seen that we have created two distilled features, distilled data set. One is the full set that has been applied without applying any without applying our deep digital framework on this data. We have trained this data as well as we have tested our full data set. As well as we have applied two distillation process. One is distill 50, another one is distill 20. That means distill 50 means 50%. We have reduced to 50%. And another 20 means we reduced our whole data set to a 20% only, right? So based on our experience, we can see that it's consistent. You see that? Like for a full data set, the exception net and the dense net. Similarly, for the DenseNet 50, this is a Distil 50, this is Distil. So all these informations are relatively, ratios are same. That means they are after reducing that without concerning the performance, our Distil after applying this Distil framework, it produces the same level of result, same type or same score, same accuracy score, right? So the result exactly demonstrated that the models trained on the Distil datasets while having a significant reduced dataset size are able to maintain the high detection accuracy, showcasing the efficacy of the Distil framework in preserving essential defect feature. In addition to that, the study also provides deeper insights into the performance metrics such as precision, recall, F1 score, that exactly highlighting the model's adaptability and the trade-offs between the dataset size and the detection accuracy in resource constraint environments, where exception model demonstrate remarkable resilience with consistently high precision and the recall values, as well as the DenseNet model maintains a high recall rate in the same way while displaying the varying precision metrics across different evaluations. So what are the key takeaways? Key takeaways is that we have introduced an innovative digital framework designed for data distillation in AI model training, as well as we have demonstrated the efficacy. So after reducing the data set, it also provides the same level of results. So why do we need to use this full data set? If we gonna provide the same type of result with a limited size of data set, why don't we use this deep digital framework, right? So our feature distribution, we know that we have a lot of limitations due to the time limit, due to the constraint, due to the infrastructure. So the deep digital framework exactly provides a structured approach to design distilled data set for effective defect detection, model training, reducing computational cost while preserving the essential data characteristics. Our study identifies the area for further exploration, such as optimizing the distillation ratio to achieve even smaller data set and experimenting with additional defect data set to validate the framework, broader applicability, and the defect frameworks lays the groundwork for future advancement in dataset distillation, that paving the way more efficient and effective defect detection models resource constrained environments. So call to action. So if you have any question, so in that case, I would say that now you might have a question, why haven't I provided the result? Like, why haven't I compared my model and compared my experimentation with existing work? So I would like to say sorry, because of there is no work has been done on this area. I mean, defect distillation on defect detection. That's that we haven't found any of this work that has been done using defect distillation, using a data distillation process. So we are proceeding further. We are doing a lot, and we will be exploring more things. Thank you. If you have any question, reach out to me. Sure.
At first, you can try any random estimate for that. It's not random. This is first person, you can try in popular experiment. And the second one, over first person, do we have any compression of the selected data? For example, we drop it to 20%, but what makes these data important for your problem, right? When I collect all the data, I don't need to distill, especially the data collection should risk. So you need to have a compression on the distilled data. So what's your takeout from this perspective?
Thank you. Thank you for asking this question. The thing is that first time we are thinking that we'll be applying this random selection, right? So randomization, yeah, we can definitely do this randomization, because our main focus was to apply the active learning. That means we are trying to exactly finding the uncertainty of each of this framework. That means calculate this framework, how this, that means first we are going to mainly focusing on the feature, how they're correlated with, mostly related with this result. Then how they are making this like a prediction, whether it is a real or fake. So we apply the iterative process, where we exactly always try to calculate the uncertainty. That uncertainty exactly provide the confidence level of this model performance. That's what we haven't tried second times the randomization, because whatever the process randomization we applied, this is just not providing a good result. That's why we move to active learning process. And Sorry, I forgot your second question. Yeah, the main concern is our consideration was to mainly, we are just trying to see that whether after distilling the data, that means after reducing the data, whether the performance degrade or not. For example, before distillation, if we see that our accuracy is like a 90%, if we see that after the distillation, if we see that the data performance accuracy is less than 90%, that means it is meaningless. We're just making sure that definitely the result should be around 90%, close to 90%. Either more than a little bit, 90 point something or 89 point something. That means if we see that the performance is close, that means no matter the data is going to reduce it, performance is perfectly working. Any other question?
Let's move to the next presentation.
Okay, so if you have any question, I will leave my card so you can reach out to me. Thank you. Thank you for joining.
Please unmute yourself.
Okay, so can you hear me?
Yes.
Okay, and hi guys, and this is Muyang He from Peking University, and I'm here to produce my recent work, large-scale dataset pruning with dynamic uncertainty. Done when I was an intern at Beijing Academy of Artificial Intelligence, mentored by Dr. Bo Zhao. And so let's start it. And this paper addressed a conventional supervised learning problem, which means we have some images and their labels, and to point out what class these images belongs to. And we want to produce a core set with a much smaller dataset size, but we have comparable performance on that. And we want to scale up this problem from to large scale datasets, which means ImageNet 1000 and ImageNet 21,000. From CIFAR 10 or CIFAR 100, we have just maybe thousands of images on that small scale datasets. But now we have to do something in a scale of million samples. And we want to expand this problem into more modern architectures, which means swing transformer, ConvNeXt, and ResNet. On that time, when I work about this work, the swing transformer is relatively new. So, and because we have a large scale, which means we have millions images, so we would like to do selection rather than distillation. Because as we all know, the distillation is much more complex than selection. And if we have about 1 million samples, we believe that we can select a core set from that because we have much more candidates, and we can just prune something and without loss the performance. So our goal is to do lossless compression about this image classification task. And we have a basic insight that we want to find more valuable data. So how to define this valuable? And we believe it is about learnable. So it shouldn't be too easy or too hard, because if it's too easy, the model can learn it very quickly, and so it becomes less learnable in the following epochs. But if it is too hard, so it is unlearnable because the model always cannot learn it. So we want to find some more learnable data. And then we will talk about how this idea produced from. So we have a basic method in this dataset pruning area is forgetting. So the forgetting counts the flips in the training process, which means the model predict the image correctly on the former epoch, but wrongly in this epoch. So it counts it as a coin flip. And so we may think about this flip, this change is 1 0 1 0 1 0 is this correct? So can we count some continuous change? So maybe we can count about the prediction logics or the loss or something. So we can count something about continuous change. And we also find a paper in the natural language processing area. It is called dataset cartography. So we can see this figure, and it's so for it cuts all the data into 3 categories, which means easy to learn, hard to learn, and ambiguous. So we have some easy to learn, which means the confidence is very high and the variance is also small. So the model learn it very quickly, so it consistently predicts it correctly. And for those hard to learn, we can see the variance is small and the confidence is also small. So which means the model consistently predicts it wrongly, and the model cannot learn something about it. So it is so wrongly and wrongly and wrongly. And the third category is about ambiguous data, which means the variance is high and the confidence is around half, which means the model are very unsure about it. And this paper point out that if we just use this ambiguous data, the model can learn a lot of information about this dataset and obtain a relatively good performance. So it points out that ambiguous data is more valuable, and this inspired us. So we think that the variance matters, which means we may consider about data, the prediction accuracy about data through the training process, and we will calculate the variance. And we believe that just like this dataset category, so we believe that if the variance is small, which means the model has a consistent cognition about this image, so which means it may be less valuable. And if the mean accuracy is also high, which means this is too easy to learn, and if the mean accuracy is also small, which means it's too hard to learn. And for those samples with high variance, which means the model is very unsure about this sample, and it may contain more information about this image classification that task. And we have conducted some primary experiments about this variance, and we found if we just record the variance through all the process, and just one data point, so we have just one variance about all these n epochs, and the result is the performance is very poor. So we think we need to calculate the whole process variance. So we think we need to include some training dynamics. And so finally our method is about the variance in a sliding window, which means for every epoch we just calculate the variance about the last k epochs. So last j epochs, which means we have a sliding window with length j, and we just compute the variance about this last j epochs, and we will average all this variance through the whole process. So So we have a variance and the mean of this variance. We believe this include the training dynamics and the prediction uncertainty about it. So if we we have this method and we do some experiments. So we can see this table. It show us our method is consistently the first, and we surpass the previous SOTA. So we can see we have in ImageNet 1K we have if we pruning one-fourth data, and we will have our image accuracy is almost the same. And for the ImageNet 21,000, we have also, if we just prune 25% data, we will almost lose no performance. And if we have draw a figure about it, you can see. So in the 25%, we have almost lossless compression, and as the pruning ratio increase, our performance drops, but drops the least. So we have compete with 7 methods. So this experimental results showed our method's strong performance before the half pruning scenario. So you can see our pruning ratio is up to 50%. So why? And we will talk about it later. So, and then I have drawn a figure about what data we have pruned. So this dataset map is just like the dataset category, and we have the whole train set is about this. So we can see we have 3 axes. For the y-axis is the mean of prediction, which means the mean accuracy, and the x-axis is about the standard deviation of predictions, which means the variance. Now we also have the color to represent about the numbers of correct predictions. So we can see for this part, it has the high mean and small variance, and we can say it has a very high correct predictions. So it is very easy to learn. And we have this part, it has a mean accuracy and a small mean accuracy and a small variance, but and also with very small numbers of correct predictions. So we can see the models almost never predict them correctly in the training. And we also have some ambiguous data. So we can see our method. So we can see for our methods and for getting, we pruned some of this hard to learn data sets. This data, and we prune a lot of easy to learn data. So you can see we have the similar insights about dataset pruning, but we prune more accurate because we combine the prediction uncertainty and the training dynamics. So we achieve the best performance. And for example, EL2 norm and entropy, we can say it prune almost all the easy to learn data. And for random pruning for SSP and for moderate, we can say they prune the data set in another dimension. So in this figure, we can see it almost pruning all 3 categories in the same density. And we can see we have for both us and for getting, we have pruning a lot of easy to learn data, and we have found that if we prune too much easy to learn data, so if we pay attention to forgetting, just like this green triangle line, and we will find it drops a lot from 40% to 50%. You can see a big drop and a big drop. So we can say So we can see that if we prune too much easy-to-learn data, the model cannot have a basic understanding of this image classification task, and the performance will drop a lot. And our methods, and although our methods perform very well, if we have the pruning ratio smaller than 50%, but if we scale up it to, for example, 80% or 90%, it will also drop a lot and will worse than random selection in that scenario. So our methods would perform very well in relatively small pruning ratio. And we want to emphasize that we can achieve like 25% lossless compression here. And also we have done some cross-architectural generation experiments. So you can see if we change the architecture in pruning and in test, so we can see our method also performs very well and can suppress the formal sorters. And we have done some average study on observation number. So for the first row, as I mentioned before, it is the dataset category method. So we just calculate the variance through all the epochs, just one variance in this scenario, and we can see the performance drops a lot. And if we combine the training dynamics, which means we average the variance through the training dynamics, the performance would come back. However, if we combine more observation of variance, for example, we may conduct 3 individual experiments about multiple initializations, or we combine 3 multiple architecture initializations in the experiments, but the performance is almost the same as this no combining scenario. So we think this observation numbers, it has a best ratio about maybe for example, if we have a 300 epochs settings, and we may observation about 100 numbers of variance, it is fine and it is enough. We don't need more observations, but if we have very small observations, it will drop a lot. The performance will drop a lot also. So we will do so. Let's conclude this our paper.
We're done out of time. Can you please finalize your presentation?
Sorry?
Yeah, we're done out of time.
Oh, so okay. I will conclude it very quickly. So we emphasize that variance with the whole process matters, and we think this method have some explorations. For example, we can use it in weak supervised tasks. For example, for LLM, and I would to say that this has been explored because the paper has been uploaded to archive, and also we can try it in the VLM area. And this method has the biggest limitation is about it have to chain multiple epochs to compute the variance through these epochs. And in this LLM area, we may chain every sample only once in our training settings. So maybe we cannot calculate this variance in this area. And that's all. Thank you all very much for listening our paper. So any questions?
No. Okay, we are gonna move to the next presentation.
Okay.
One of you suggested to have a very quick coffee break. It's up to you. So raise your hand if you'd like to have a coffee break. Just 2%. So that's. Oh, okay, that's why. I mean, it's far away there. Yeah. Okay, let's move to the next one. Next one would be checkmate efficient video summarization by checking mutually averaged temporal scapulation. You are the one. Sure. Yeah, I have your presentation. PDF would be nice. If sure. Sure. Try to find this. Yes, of course. Thanks. Yep. I'm trying to minimize this guy. Okay. Hi everyone, I'm Fahim, and let's go back to our task. So we're presenting Checkmate. So Checkmate is for video summarization. So task is like this. So think about action classifications where we have the video data sets and we use 3D models for the action classification or video classification. So it is a problematic because we convert the image models into 3D models, which is very expensive when we train things. Especially when it's supervised or self-supervised in any case. So the challenges are like this. When the 3D models we're going to train, it takes 2 weeks to months for training procedure. So because of this, training 3D models for the action classification is hard. So we are thinking the problem in a way, can we actually reduce the problem into more easier version when we do not have to use the video models or do not have to use the videos at all for the training procedure. But in the test time, we will use the videos for our task. So task is like this. You have a video and you summarize or distill the whole video into a single frame or 2 frames or n frames, depending on your choice. And then you train your classifier on the based on a summarized frame or summarized set of frames. Then you, during the test time, you will take your test streams, which is the real videos, and you pass it to the image classifier and you see, can you classify your actions or not? So this is the whole purpose of this task. So how do you solve it? So the procedure is like this. If we have a video, and we take clips out of it. During the video summarization, during the video classification procedure, what we do, we take n clips from the videos during the whole epochs. And in this way, we get to learn about the whole video altogether. So what we do the same, but we do it for the only 1 frame. So what we do is this, we take n clips from the videos and we get the representation from those videos based upon our backbone model. And we have a summary image or summary frame. And we also get this representation with respect to the backbone. So catch is the backbone is pre-trained. And for example, for this task, we have used COM-NEXT. So we're asking this question. So given the COM-NEXT, if you pass the summary image, you will get a representation. And given the COM-NEXT, you will pass the videos or video clips, and you will get another representation. And if you minimize the loss function between the representation from the video clips and your representation from the image, will that become the same? So that's the whole task. So in this procedure, we backpropagate the gradients only to the summary image. So we update the images and it becomes our summary of the whole video. So the training procedure is like this. and we have a frozen backbone, and we pass the video, and we get the representation, which we call the video encapsulation. And we also pass the summary frame, we get another summary frame encapsulation. We perform simple mean square loss minimization. And in this way, we update our summary frame. So this summary frame contains all the information of the video. So we do it for each videos. So that means you have 10,000 videos per data set. You have 10,000 summary images or 10,000 summary frames. So summary frames could be 1, 2, or 8, depending on your choice again. So then we train the classifier based upon the summary frames. And remember that we kept the backbone model during the summarization and during the classification procedure same. We did not try the cross-architectural procedure, and it has some limitations. I will tell it later. And during the test time, since our classifier is trained with the summary frame, during the test time, we pass the normal videos and get our classification performance. So let's get back to the results. So in our results, in the checkmate, we have tried with that summary frame 1 and summary frame 2, and so 2 summary frames maximum. So our performance is nearly up to the mark with respect to the IFS. So IFS is so far available the best performing video summarization, and they are using 8 frames. So their performance is 97 and 98, depending on the modality they have used. And in our case, it's 80 and 93. By using 1 extra summary frame, we can get up to 13% boost. And this was also same for the HMDB51. Yes, you can disregard the performance for the UCF101 because it is MNIST for video classification, but HMDB51, it is a complicated data set. Yes. So in this case, also we also get the better performance. And you also get to know that we do not use any flow information as a support, or do not use any kind of kinetics pre-training as well, which is being prevalent for other data sets, sorry, other models. So this is for the regular classification. And now we look into the fact that what we have learned from this task, can we transfer it for the low dimensional cases? Yes, we can do it. So in the case of the low dimensionals, for example, extremely low, 16 by 12 or 28 by 28, if you reduce the dimension of your data, so we also get a very good performance with respect to the other ultra low dimensional action recognition models as well. And this trend continues for the UCF101 and HMDB51 as well. Remember that we do not have to re-summarize everything together. We just downsample our summary frame into the 16 by 12 or 28 by 18 and do the straight classification, and we get this performance. So that means whatever the cost you have been through during the distillation procedure, it is one time. You do not have to do it multiple times depending on your training budget or dataset requirement. So that's the whole results so far from the checkmate. But the takeaways are, for each summarization procedure, or for each video, we take 4 seconds. Our GPU was 3090 RTX, and our backbone was fixed. We did not try cross-architectural. So for other results, but we did try unofficially for the Connext. We have used the vision transformer, but we did not get the same performance. It is because our feature space was only meant for the Connext. So that means if we use vision transformers, we cannot actually match or reach that feature space together. So that's why the performance is not up to the mark, but we can look into it, and we have left it for the future work as well. And frames, this is interesting. More frame actually brings more performance, but we are not sure that first frame and the second frame, are they the same information or they are different information? We are not sure about it. We also left it for the future work as well. And Kinetics 400 and 600, we also have left it, but there isn't one update. Recently, I have performed task on the Kinetics 100, and it was like 78%. So I think if I extend the work for the Kinetics 400, I will get better performance as well. And the cross-modal performance, I have told you before, it is not satisfactory as well, and I think it is not satisfactory for all the dataset distillation tasks as well, because we always rely on the random initialization or the pre-trained model. So whenever we are using the pre-trained model, we're strictly fixing our optimization landscape to that pre-trained model only. So that's all I have to offer for this work. So I'm ready for question if you have any. Thank you very much.
Any questions? Okay, let's move to the next
1%.
Yep,
Yeah.
go ahead.
Yes. Yes.
I missed one of the points on the frame. So
Yeah.
are you using more frames when you train, kind of say here like reference to use, or are you using more frames to summarize the PDF?
More summarize. Yes, it is also used for training as well. For example, if you have 400 frames for a given video, you are summarizing into one frame or two frames or 8 frames. For example, IFS 3D, they have summarized the whole video into 8 frames. And we have summarized the whole video into one frame and two versions. So that means we have 2 data sets for the whole video. So if we use 2 frames for training procedure, we get the better performance. But if we use 1 frame, that means it is straightforward image classification task. So it is, yeah. But for the 2 frames, it is a little bit tricky because you have to done a for loop for the representation extraction. Then you summarize and get your softmax and get your result. So that's the caveat on it. Yeah.
How do you know 2 frames are summarizing the video?
Yes, yeah, the more thing is like, is this, so it is coming from the data distillation that the more images, that means the more representation is compacted into the more images, right? Because they are working at the initial point for the whole data sets. That means more frames are actually the more initial points for you, the whole videos. That's the main point. But if you look into the perspective, if you look into the fact from the perspective that are they summarizing the similar information into the both frames or the different information, we are not sure about it. We have to inspect it and say more clearly about it in the future work. One thing is this like you can do separate classification on them. For example, first frame, you do the classification, what is the performance, and second frame, what is the performance. And another thing is definitely the GradChem like works. So for example, if you do the classification, if you try to see where the action overlapping is happening, you will know for sure that it is signifying this information only, it is signifying that information only. Yes, that's my answer for it. You're welcome. And no more question, right?
We don't have time for
other
questions.
Thanks.
I think next one would be Dyna Distill, leveraging real-time feedback for effective dataset distillation by Zhang Chen.
Yeah, it's me. I need to attend virtually.
Sure. Okay, let me cancel here on my share screen. Yeah, go ahead, please.
Okay. Let me share the screen first.
Try to find us your presentation in 10 minutes. Thank you.
Can you see my screen?
Yes.
Okay, and can you hear me?
Yes.
Okay, now I'm Zhong Xiongcheng, and I'm a researcher at Fraunhofer Focus, Germany. And today I'm very happy to present our work, Dyna Distill, leveraging real-time feedback for effective dataset distillation. And this work is cooperated with Derry Zhu, Jiahui Geng, and Soya and Manfred. For dataset distillation, it's the objective of dataset distillation is to compress the knowledge contained in the original large-scale dataset into a tiny synthetic dataset. And we can formulate the dataset distillation as the least objective. And in this paper, we just integrate our method into current state-of-the-art approach that's matching training trajectory, informative dataset condensation, and effective data distillation by bidirectional representation matchings. And these 3 methods cover the trajectory matching and gradient matching, also for distribution matching. Our motivation is that to obtain a distilled cipher 10 with 10 image per class. So for the MTT, we need about 250,000 iterations. And for the Dream and the IDC method, we also need 200,000 iterations. So this method have, and we also find that those methods have large oscillation in their training loss, and such will fluctuations implies that some initialization of model parameters at a specific distillation step may degrade the performance of the synthetic dataset. And our goal now is to reduce the overall distillation or optimization steps while preserving the performance of synthetic dataset. This is the overall workflow of our method. Apart from different from previous works, we construct a pre-trained models and trajectory pools, and at each distillation step, so we will evaluate. Since we have a collection of pre-trained models, so we can evaluate the synthetic data set at a specific distilled step and select the best trajectory or models from the candidates and learn learn to improve the overall performance, and so that we can reduce the training and reduce the overall optimization steps. And here is the algorithm. On the right side is the algorithm of our method. First, we will randomly initialize a distilled data set and randomly initialize uncandidates networks. And for each network, we will train on the real data set for specific epochs. And now at each distillation steps, we will random select M networks from the candidate networks and evaluate it. And we will sample a small portion of the network from the candidate from M networks according to the loss, and perform the original distillation algorithms such as the MTT or IDC or Dream Plus. Our experience setup is follow the previous works. We use the Cypher 10 and Cypher 100 dataset, and we also use the COFNET 3 to distill the synthetic dataset. And for the training details, we build on top of other like MTT, IDC, Dream Plus repositories, and just integrate our algorithm into existing repositories. Here is our experiments. We can see that our method can a bit slighter have a slight improvement compared to the original versions. Except for the Dream Plus, and we think maybe it's due to the IPC is very small, so yeah, and maybe the difference is also still the difference is still very near. So yeah, and for the cross model cross architecture evaluation, we also find that our method can slightly beat the original versions. Like here, all the best performance are marked as broad. And here, from this picture, we can see that we can reduce the overall training optimization steps. For the 95%, it's the peak accuracy of the achieved in the original method, like Dream Plus. And we can see that in the original Dream Plus, it take around 160 steps, training steps to achieve 90% accuracy of peak accuracy. And for for our method, we just take around 30 training steps to achieve that accuracy. So if we incorporate our method, we can just stop at 30 30 steps, and in these terms, we can reduce the overall training times and to improve the training efficiency. On the right side, it's for the result for the IPC10. We can also see we observe the similar results. We obtain the similar results. And the conclusion is that the advantage of our method is that we can reduce the overall optimization steps and enhance the performance of the distilled data set. And we can integrate with existing surrogative objective-based frameworks such as trajectory matching and gradient matching and distribution matching algorithms. Since we need to evaluate lots of pre-trained models during the optimization, so it will require require a vast demand of GPU resource. Thanks. Any question? Hello? Host Chair, you are muted. Hello?
Hello, it's muted here. I'm just a listener. I think we don't have any question. Thank you.
Okay, thanks.
So you're closing on your laptop, right? You're presenting which one? All the schools, like, and a data-centric approach with the author here is here. Well, how do you present on your laptop? Okay, after
because the Zoom seems they didn't change the screen. It's still here.
Okay. You'll have to do so. Hello. Yeah, it's updating, I think we had some issues. But I'll continue with that. So basically, the idea is in semi-supervised learning, there's a way, the three scores that I talked about in the previous slide were all about based on supervised learning, and the drawback there was that basically you had to train to be able to get these scores out. The simplest score that I know of, which does not require training, is based on this idea that you take a pre-trained self-supervised model, define the difficulty of each example by the distance to its nearest cluster, right? And these are the easy examples of the most prototypical. So here you're assuming that you have a self-supervised pre-trained model available, but on this data set, on the data set that you're working on, you do not have to do any training to get this score out. The questions that have been raised in literature, and this is kind of for any of the things that I talk about, whether it's curriculum learning, whether it's pruning or active learning, the questions that have been raised is that one observation is that which was there in, I think, a couple last year's Europe, was basically no score really performs well except the ones which are the most computationally intensive. So the only one that I think does well is EL2N, or there are examples of scores which are even more computationally intensive than that. Those are the only scores that these people showed that work well with ImageNet kind of data. So a lot of people, including me, will show results on CIFAR, but this NeurIPS paper last year did experiments on ImageNet scale, and they showed that none of the scores are doing very well. They asked these questions: what is the nature of the examples that can be removed? How early in training can we recognize such examples? How many examples do we need, and so on and so forth. Basically, from this, these last three conclusions sort of derive this thing. We want a score which is very simple in computation. The other thing that I want is basically I want the score to rely just on the input, not on the input and the label. Even in the prototypical T score that we talked about, the self-supervised learning, basically there's a clustering happening, and you get a pseudo label from the cluster, and you're using the pseudo label to get the score. The score that I propose is basically the entropy of the image. It's a very simple idea. And I'm going to go through why this is perhaps the most important slide I have. I'll just go through this quick in some depth. The reason I use this is that I want to the motivation. First motivation is that images with less clutter are processed faster with the human visual system. This is a fairly well-known fact. It has been. So if you are standing against a white background, or a fish or something, it is true that the human visual processing will happen faster than if you're standing in a crowd, for example, right? Simple this thing. Clutter can be captured by the entropy of an image. Again, something that has been known. There are multiple papers on this. So higher entropy, more clutter. One of the other second motivation is basically learning from some images which have less clutter.
lead to better labeling of pictures by young children. So if you look at children book, you'll see that a lot of children books are basically iconic images, what they call iconic images, white background and some object on that background, not even multiple objects, right? 2-3 years old basically learn a lot from the iconic images, and there have been studies which basically show that they learn better from such iconic images. In NLP, the length of a sentence or the rarity of a word in a sentence is a good score. People in NLP have done that. For example, in machine translation, they've said it is easier to learn you could use a score like for pruning or for curriculum learning, where you basically the length of the sentence is going to tell you how difficult it would be to translate. The last is something I came across very recently, and the idea here in basically in flow-based generative models, you can they have observed that the entropy of an image and the likelihood of generating the image in flow-based model, you can actually calculate the likelihood precisely. So entropy of an image and likelihood of generating image are negatively correlated. So if the entropy is large, it is more difficult to generate the image. So this is again kind of related to clutter, and if you look at the fourth point, the first point, it kind of makes sense. And this idea is being used for out of distribution identification. Yeah. Okay. Basically, I proposed to use just the entropy of an image. What I wanted to experiment with, how well can you do by just looking at the entropy of the image. I don't have any labels. It's totally unsupervised, just the entropy of an image. And the way I calculate the image entropy of an image by looking at the bits per pixel. So there's lots of words in the slide, but the idea here is that if the main proposal here, the entropy if it was a lossless compression, it's definitely upper bound the entropy by the bits per pixels of an image. So total bits divided by the dimension of the image. If it's not, assuming that it is nearly lossless and distortion is not high, you can still kind of assume that the bits per pixel is going to give you an estimate of the entropy. This is a problem that this is an assumption, and it is a problem that I'm assuming that the images that are available to me are not heavily compressed or are compressed to the same distortion level. If they're not, then comparing them across multiple images is not going to make sense, right? So if you have to assume that the distortion is low, and you have to assume that this thing. So there's the issue here which can run into practicality. If you have images coming from different cameras, you could have different compression ratios and so on and so forth. Computer vision data sets, and especially the ones that I have considered in this paper, they are mostly compressed fairly low, near losslessly. So they don't have that many compression artifacts. And we'll look at some of the artifacts that come up. For CIFAR, so here I'm showing you the lowest entropy images, basically. You can sort of think of that. CIFAR, you see that they're basically iconic images for each of the class, very simple images if you are this thing. The other, on this side, I've shown the iconic images for walk data set. So just to compare, one of the other things that I've done in this paper is not only talk about image classification and data-centric for image classification, but also for semantic segmentation. Basically, because we'll sort of see why I went into that as we go along. CIFAR, the highest, the entropy images are obviously much more cluttered. Similarly, for walk, you can clearly see the difference between the lower entropy images and the highest entropy. Now, all this is great, but basically what it leads to is bias. So I'll talk about the bias in a minute, but let's just start by, I took the example of taking the ship images in CIFAR, and these are just random images, some, I guess, 16 random images from CIFAR of ship class. If I choose the same using my entropy method, either I choose the lowest 16 or the highest 16, you can clearly see that these are very self-similar, right? Or you can also see that the fact that they're actually, the lowest is all like distant ships, they're all blue, they're very, very similar to each other. Even the highest entropy images are quite similar. They have clutter, they have a particular pose, or most of them. They're not as diverse clearly they're not as diverse as a random thing. So therein lies the biggest problem of sort of this. Turns out that this problem is it's the worst when you're choosing entropy. It's by far the worst when you're choosing entropy, but it's there in the other scores also. So a consistency score, if you're choosing low consistency, easy images using low, those are also fairly self-similar, right? So if you kind of take this data set, it's kind of going to learn, blue is water. It's kind of going to learn, blue is water. Sorry. Then, so this is for consistency. Prototypicality is actually, the low scores are still okay, but the high scores are very similar to the ones that we see in entropy scores. So again, there is this idea that there is a bias built. What I'm trying to motivate by these 3-4 slides is EL2N, again, the low scores have very similar images. In fact, there's a repetition of they say. What I'm trying to motivate out here is that the moment you select, if you're not randomly selecting, you are biasing yourself. And this is the reason why when you look at any of these papers, sure, for very small data set, there's often you can see some amount of improvement over random. But for if you prove, if you select, for example, CIFAR, if the example that people give you 1,000 images, yeah, sure, some improvement over random. But the moment you have 10,000, but the accuracy drops off, right? And the moment you get to 10,000 images, random does better than any of these scores, just because of this bias, because of the fact that the images that it is learning from are all very similar. So to remove the bias, I basically used a method, a graph sampling method. Now, there have been other papers on graph sampling. I use a method which was proposed way back in CVPR 2012. There have been recent papers. One of the things that I have to say before anything else is when you start sampling, it is that basically you're starting from perhaps from a sort of you chose a high prototypicality score, but you're sort of whichever way you sample, you are moving it towards a random data set. So one of the you start with a very structured choice, and then when you start sampling to make it diverge, you are moving towards a random data set. So that's one of the issues of the sampling method. So I think there's something else that needs to be done when you are. What I'm trying to and the LLM people, it seems, have sort of, at least from what I understood, is they have figured it out by sort of doing some ad hoc methods for training. As I said, they iterate over certain parts of data set multiple times, and they don't iterate, and they use certain parts of the data set only once. So the graph sampling method, anyway, coming back to the graph sampling method, a KNN graph is built. Each image is a node, and each node has k edges. Score of an image is attached to the corresponding node. Basically, the idea is that you create a KNN graph. The moment you select a node, you ensure that the scores of the neighboring nodes is down-weighted. So once you selected an image or a node, its neighbors will not be selected. So self-similar, its neighbors will be the ones which are similar to it. Those will not be selected just because you're going to downweight its immediate neighbors. Now, the distance in the graph, you could use the embedding space. Again, like the self-supervised model that you talked about in the prototypical scores, you could use the embedding space. One of the interesting ones that I used for semantic segmentation was basically the Wasserstein distance. Basically, I took the histograms of the semantic labels. So I took 2 images. So right here at the bottom, you see 2 images, the semantic labeled images. One has a horse, one has a train in it. And I took the semantic, this semantic image, and I took the histograms of the labels, and then I found the distance between those 2 images, right? So basically, in the semantic space, how different are these 2 images? What is the distribution? So this is kind of related to the color histogram and color method that was used in image retrieval earlier. One of the things that you see, if you use this method, this is a new method, the semantic label distribution method, you'll see more diversity again. So if you use semantic labels to define your KNN graph, instead of using embedding space, you find more diversity, and which is good for us. Coming to the results quickly, basically for image classification, bits per pixel did really badly. You can see that they're not even the ballpark, right? So by itself, entropy did pathetically. So it's not something that it wasn't a very great result. Only by adding graph sampling to it that I was able to get it near random, but not much more than random. So image classification, my method of using entropy as a way to select images and then doing graph sampling kind of got it to some reasonable number, but nothing great. Semantic segmentation, on the other hand, we have some decent results. Firstly, semantic segmentation, I do not know of, there's not been that much work on data distillation or data centric, but it's an important topic, specifically if you think about it in terms of semantic segmentation of satellite images. So it's something that we are working on. So in semantic segmentation, we basically we're showing the number of samples we selected to train. We're showing the pixel accuracy on the y-axis. And we were able to beat random for all the distinct except for when we started taking large number of samples, right? So we were this semantic label method that labeling method for histogram that I just talked about, that bits per pixel was able to beat random for all for low number of samples. One of the things that we in semantic segmentation, the clutter matters a little bit more than image classification. So I definitely this result makes sense. Similar results for AD data. We took the AD 20K data, 20K data, I think. And we got similar results. There, again, we'll be able to beat random fairly easily. In both these, also in semantic segmentation, the interesting result was that prototypicality did not do that well. So prototypicality, which is a reasonably good method for ImageNet, which has been shown to be a good method for ImageNet classification, did not do well for semantic segmentation. Conclusion, bits per pixel is a simple measure. Can be used only if there's low compression distortion, lossless compared. It is highly biased. So one of the problems is that it is highly biased. And there must be some way to remove the bias, make it more random. In some sense, you're moving it towards more random. Random wins because it's the least bias. The way I think the biggest future work here is that can you use this method as a prior? You know, all the score that you've calculated, if you start with the entropy as a prior and then kind of use, because on all those methods, you're actually using the labels and you're training. So you start with this method and then train. Will you be able to do well? Is what my future work is going to do. Okay. Any questions? Thank you.
Okay, sorry. So for step B, we're going to train the model on the subset that we selected in step A. And finally, we're going to evaluate the student clip model on the target task. So on the bottom right, we show a chart comparing our problem setting with prior OOD problem settings, such as domain adaptation, domain generalization. In particular, compared to domain generalization, DG works use some either unlabeled or labeled task-specific source data, while we're using task-agnostic source data. So, summary for contributions, mainly for the subset construction problem. We propose a novel sample selection scheme for building a representative subset of the source data for a target task. We included theoretical discussion on the challenges of cross-modal approximate nearest neighbor search, which is required for the retrieval step in step A. We propose a paired k-means clustering algorithm for building index with better cross-modal recall. And we also propose a unsupervised adaptive label augmentation scheme to build a more diverse subset of the source data. For step B, we also propose a diversity preserving loss to prevent collapse of the clip features during training. And finally, we compare with state-of-the-art results in comparison to current zero-shot and source-free domain generalization methods. So our method overview consists of 4 steps. The figure on the left here illustrates, so first we calculate the image features corresponding to the source data, and this is illustrated by these gray circles on the left. The next step is to calculate the target class, the target label text features. In this case, we're doing a panda versus chihuahua classification problem, so these are illustrated as stars. We have to augment the text features in order to obtain a diverse training data set. This is illustrated using colors here. And we're going to extract the nearest neighbors of these augmented text embeddings, which we illustrate here. So we're just going to keep these nearest neighbors as a subset. And we're going to pseudo label them according to whichever text feature the image feature is closely ranked to. Step 3, we're going to cluster this subset. The purpose of this step is to select representative samples instead of training on the entire subset that we selected. So we cluster it, and then we're going to randomly extract a sample from each cluster as highlighted and just keep those samples. At the end of this procedure, what we get is a small subset that's specific to the target task, but also represents the diversity within each class. So we hope to get this type of data, and then we fit the model to that data. The next 3 slides will be some motivation for each step that I presented. Firstly, for diversified retrieval, on the left, you can see the left side of this slide is what you will get using naive nearest neighbors retrieval. So just retrieving the closest neighbor to each target class name, and what you get is just these stock photos for each class. And clearly, if you train on that data, you would severely overfit. On the right is the data obtained by our diversified retrieval procedure. And as you can see, we obtain a nice selection of diverse images that you would expect to find in the wild. In these t-SNE plots up here, we further illustrate the advantages of this diversified retrieval. So the blue dots represent what you would get just by extracting the nearest neighbors of the target class names, and they and with this diverse retrieval procedure, we get these orange dots representing a broader spectrum of target concepts. So the motivation for the clustering step is that the orange dots contain many semantic duplicates. So if you see it, some places are close together, and also the label distribution is not uniform. So our solution to this problem is to cluster the images into K clusters and then randomly select one from each cluster. And this results in a subset of images that both covers a broad spectrum of label concepts, but is also representative of the image distribution. And this is represented by the green diamonds in the t-SNE plot. And then very briefly, some motivation for rank pseudo labeling. So we could just use naive cosine similarity pseudo labeling, which means just label each image with this the closest target text feature. And this sometimes works, but there's in some data sets, there's this hubness effect where one text feature is close to many irrelevant images, and this is bad. In this example, this is for iWildCam. There's this label called empty, and a lot of these camera trap images are mapped to the label empty. And this is clearly bad. So in order to achieve a more balanced pseudo labeling, we use retrieval rank instead of cosine similarity to determine the pseudo label. And this mitigates this hubness effect. So next two slides I'll skip over real quickly. It's since the workshop paper submission, we've developed two more innovations to our pipeline. One is a novel paired k-means indexing scheme, which deals with this modality gap between image and text features. And using our novel paired k-means indexing scheme, we can achieve better cross-modal recall. And we also developed this novel adaptive label augmentation scheme, which is a better label augmentation than the state-of-the-art label augmentation schemes such as waffle clip and classification by description. And this achieves better zero-shot accuracy. So our results are better compared to state-of-the-art zero-shot methods and domain generalization methods. And in summary, I presented a applying of 3 steps in order to construct a subset of the source data set for multimodal unsupervised domain generalization. And we publish our code on GitHub in this link, and also we have the archives submission at that link. Any questions? Thank you.
Hello? Hello? Is anyone here? I can't hear anyone.
Okay, Ruyao, it's your turn, but the host is not here. Can you share your screen and test your
Okay.
voice?
Can you see the screen? Can anyone hear the slide? If there is no problem, then I will start my presentation.
We cannot hear you at present. Can you see something to test your voice?
You can't hear my voice, or just cannot see my slides? Hello? Hello?
Okay, Liu, can you say something to test your voice?
Hi,
We change the
can you
volume.
can,
Okay.
can you hear me?
Yes, we
Yes.
can.
Okay, okay. Then I will begin my presentation. Hi, yes, this is Yao. I'd like to share my recent work exploring the impact of dataset bias on dataset distribution online. Let me first introduce the dataset distribution, which aims to compress large datasets into smaller ones to improve training efficiency. Lots of subsequent study has proposed a series of methods to improve the performance of synthetic datasets, including grading matching, trajectory matching, and distribution matching, and so on. So to despite achieve sorry. So despite achieving significant improvement, existing DD method usually operate under the presupposition that the dataset is unbiased, overlooking potential issues within the dataset itself. However, in reality, datasets can be fought with various problems. One of the most important one is the dataset bias. So let me introduce the notion of dataset bias first. For example, see this picture. Many images labels as camera may contain a desert background. This unintentional correction will mislead the model into associating camera with desert instead of learning the actual characteristics of a camera. Samples that have a strong correlation, like camera in the desert, are called bias alien samples, and while samples that have a weak correlation, like camera near the sea, like this picture, are termed bias conflicting samples. Now, so existing DD methods do not take the dataset bias into consideration. To fill in this blank, we aim to investigate the influence of data bias on DD. First of all, we create two biased datasets for DD, named C-minus DD and C-10 DD, following the instruction of Nam et al. Each dataset consists of 6 training sets with varying biased rates and one unbiased testing dataset. Finally, a parameter severity is introduced to regulate the intensity of disturbance on C-minus DD and C-10 DD. And the biased rate is calculated as follows. This formulation. NBA and NBC denotes the number of bias alien samples and bias complicating samples respectively. So this is the visualization of the our data set. This is the unbiased one. These two, figure A and figure F, are the unbiased one, and figure B to E is the biased one on C-minus DD. And the right figure G and to figure J is the biased images on CIVA10DD. From servability increase from top to bottom. So why do we need to build our own biased dataset? That's it, because the existing biased dataset exhibit a high level of bias, like 95% at all, and but which is not conducive to comprehensively analyze the impact of dataset bias on DD. In construct, our bias rate covers a wide range of bias rate, range from 0% to 100%. So our dataset is more suitable for analyze the dataset bias in DD. So in this paper, we select 3 representative DD methods for experiments. Gradient matching based DC, DSA, and distribution matching based DM. One can use the more SOTA DD method to reproduce our method too. And specifically, DC aliens training grids derived from synthetic samples with those obtained from original samples. On the basis of DC, DSA further applies the data augmentation techniques to improve the performance of synthetic dataset. DM use the aliens the future distribution of synthetic and real training set use the MMD in sampled embedding space. Then here is some experimental results. We use the default hyperparameter setting of DC, DSA, and DM to synthesis dataset. Each one is 5 images per class. On C-MINIST DD and C-CIVA10 DD. Specifically, we use dataset with bias ratio of 0 and 1 at the severity level of 4 to conduct experiment. We find that when the bias ratio is 0, digital in the same class have complete different colors. However, when the bias ratio is 1, which digitals in the same class share the same color, which reveals that the color attribute has indeed been encoded into the synthetic dataset as a significant feature. As for CIVA10 DD, synthetic dataset generate from the biased dataset exhibit less diversity and richness compared to those derived from the unbiased dataset. We believe this phenomenon can be attributed to the bias in the original dataset that skew the distribution of features. So after that, we generate corresponding synthetic datasets, use datasets with different bias ratio, and evaluate their performance on unbiased testing data. DD is less affected by the dataset or even benefit from it at a low and very high bias rate, which can be seen from here and here. But in most cases, the dataset considerable impact DD, which highlights the necessity of identifying and mitigating bias in the original dataset during DD. The other situation is mainly the result here, which shows the dataset bias impact DD. So to divide the impact of servability on DD, we conduct a series of experiments using DM by addressing the severity of the bias training set from 1 to 4. We generate corresponding synthetic dataset and subsequently evaluate their performance on an unbiased testing data. We find that biased datasets are more susceptible to the increased disturbance severity, resulting in a more significant performance degradation than their unbiased counterparts. So finally, in the previous sections, we have demonstrated that dataset bias doesn't affect DD, and the vanilla DD method fail when faced with the biased dataset in most cases, which indicates that the linear definition of DD is no longer suitable for biased dataset. To this end, we reformulate DD within the context of the biased dataset, which we call the biased DD. And this is the formulation. Let TB, XJ, ZGJ, ZBJ, and YI be the set of the biased alien samples, where XJ and YJ are the J's biased alien samples and its label, and the ZGJ and ZBJ denotes its unbiased attribute and biased attribute. Similarly, the set of biased complicating samples can be formulated as TG, where X consists of XK, ZJK, and YK. Oh, sorry, this is YK. The objective of biased DD is to extract and retain the unbiased attributes ZG from both biased set TB and unbiased set TG, while minimizing the impact of biased attributes ZB, which can be formulated as this. Where AG is the composite of unbiased attributes presented in both TB and TG, and AB is the collection of biased attributes within TB. So we here just give the formulation of biased DD. We will leave the specific implementation of biased DD to the future work. So if you any questions? Hello? 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 Hello?
Okay. I think we don't have any questions here. And thank you for your presentation.
Okay, thank you.
The next should be Dataset. Distillation can be like vodka. Is Chen Xuxin here?
No, I'm the last
Okay. So I think you can go next. Okay, it seems that Chen Xuxin is not here, and we will go to the last one.
Test. Okay. Center view. Okay. Just one moment. I need to share that on Zoom. Okay. Can people on Zoom type in the chat or give a thumbs up so I know that you can see it? Okay. Okay, cool. Thank you. I'm the last one, so we are almost there. All right. Hello, my name is Xiaodan Du. Today I want to present our work, intrinsic LoRa. So large-scale generative models, including autoregressive models, GANs, and diffusion models, can produce high-quality, hyperphotorealistic images. These models may seem to have increasingly sophisticated understanding of the three-dimensional world. And our work is about testing to what extent that this is true and how that knowledge can be extracted from the models. In this paper, we hope to explore and answer two main questions. First, what underlying knowledge is presented in different types of generative models? And second, can we find a unified method that can extract this underlying knowledge easily from these generative models? To answer these questions, we'll propose a LoRa-based method named intrinsic LoRa and conduct thorough studies of what it can do. I'll now go over our findings one by one. First, the method proposed, intrinsic LoRa, or iLoRa for short, is capable of extracting various scene intrinsics across a broad spectrum of generative models. So first, let me do a brief recap of what is LoRa, or low-rank adaptation, for people that are not familiar with it. LoRa is developed for efficiently adapting a model to a new task or domain. With LoRa, the original weights are frozen. Input activation A is multiplied by a pair of rank decomposition matrices and added to the original output to form the new output. Since D star is far smaller than D1 and D2, LoRa is very efficient. So recently, LoRa has been applied to image synthesis models for learning new concepts or styles. We, however, apply LoRa for image intrinsics extraction tasks. Our model, intrinsic LoRa, can extract image intrinsics from all kinds of generative models, including autoregressive models, GANs, and diffusion models. Here, I use stable diffusion as an example to illustrate our pipeline. We start with a frozen pre-trained UNet and initialize LoRa adapters on top of its attention layers. During training, input image is encoded and the clean latent embedding of an image is passed in the network. The model accepts a text input, which is not important for our task. We input the name of the intrinsics, for example, surface normal as the prompt, but it really can be anything. We then encode the ground truth intrinsic maps into latent and minimize the MSE loss between it and the predicted latent. We use the supervision to update the LoRa adapters, with everything else kept frozen. Thus, the UNet is repurposed into a dense label predictor instead of a noise predictor. During inference time, given an input, its output can be directly decoded by the original decoder, treating intrinsic maps as a special kind of image. The same method can be used to extract not only surface normals, but also depth, albedo, and shading with dedicated sets of LoRa's. So here are some scene extraction results from stable diffusion UNet with iLoRa on unseen images. Note that our method successfully identified the surface of the table in the first row there, while the off-the-shelf supervised method failed to do so. We show that the same method also works on different domains like a bedroom and faces, and different model types such as VQ GAN, style GAN, and style GAN XL. So we now move to our second contribution, which is related to dataset distillation. Training of iLoRa is highly efficient, requiring only a small number of new parameters and samples. So with as few as 250 samples, iLoRa captures surface normals. We observed the best performance with 4,000 samples. iLoRa is also parameter efficient. LoRa with rank 2, which is just 0.04% of the total parameters of the stable diffusion, gives reasonable results. Our experiments show rank 8, which is 0.17% of the total parameters, give the best performance. So thanks to its efficiency, iLoRa enables data distillation through generative models. So first of all, through the generative prior, one can learn by adapting with LoRa adapters to predict image intrinsics with a small fraction of the entire data set. And secondly, generative model distills the data without explicit supervision during training. And we recover that properties with just a small nudge. The high efficiency of our method distills a large image intrinsics dataset into small LoRa modules that is only a couple of megabytes. So one of the most interesting findings of our work is that the quality of extracted intrinsics is correlated to the quality of the generative models themselves. So here we show two graphs. We apply iLoRa on 3 different generative models, VQGAN, StyleGAN V2, and StyleGAN XL, that are all trained on this FFHQ phase dataset. For both surface normal and depth prediction, error rises with model that has higher FID scores. This correlation holds true for a broad range of error metrics. The observation of this correlation between the quality of the generative models and the accuracy of the extracted scene intrinsics remains true for stable diffusion unit as well. We conduct an ablation study of various stable diffusion versions. Our analysis includes a randomly initialized UNet and the stable diffusion versions 1.1, 1.2, and 1.5. Each demonstrating significant enhancements in image generation capabilities, which in turn improve the fidelity of the scene intrinsics extraction. If you are wondering, in case you are wondering if iLoRa can be extended to multi-step diffusion, we have shown it is indeed possible with some additional tricks. For more details, please refer to our paper. Finally, the 3 main takeaways of these presentations. First, generative models implicitly learn physical scene intrinsics. Second, tiny iLoRa adapters are able to extract this information with little additional effort, which enables dataset distillation. Last but not the least, more powerful generative models give more accurate scene intrinsics. Thank you very much for listening. For more information, take a look at our paper, our project page, and the GitHub repo. If you have questions in the future, my contact info is to the bottom. And this wraps up this presentation and the whole workshop. Okay, thank you very much. Okay, so this is the end, right? I think. Sorry? Yeah, there's nothing after this. Okay, for people on Zoom, I think we're done here. I'm gonna end this meeting for now. Thank you.